How could space-time tunnels circumvent vast interstellar distance barriers? What physical conditions might birth traversable shortcuts between distant stars? Which observations could reveal evidence of cosmic doorways in space-time? In the stillness of a clear night, under a canopy of stars, you can almost hear it, a faint whisper from the depths of the cosmos. It's as if the universe itself is softly speaking, sharing a secret hidden in the darkness. The sky above is endless and silent, but in that silence, your imagination begins to wander. With each shimmering star and each delicate swirl of the Milky Way, a thought gently takes shape. Could there be hidden pathways out there among the stars? Paths we cannot see, yet somehow quietly beckoning. We gaze upward and feel both small and curious. The distances between those stars are vast, beyond measure. Light takes years, centuries, even millennia to travel from one point to another. Our nearest neighboring star is so far that its light, moving at the fastest speed the cosmos allows, spends over 4 years crossing the emptiness before it touches our eyes. And beyond that star lie countless others, spread across a universe so immense it defies full comprehension. Standing under this sky, we often wonder, how could we ever bridge such enormous gulfs? With the technology we have today, even the nearest stars remain far beyond our reach within a human lifetime. Our fastest spacecraft, hurtling through the void, would still need tens of thousands of years to arrive at our closest stellar neighbor. It's a humbling thought. The cosmos is vast and indifferent to our small, slow journeys. In that vastness, distance can feel like a solid wall, gently reminding us of our limitations. But where facts present barriers, our minds begin to seek a way around them. In the face of such immensity, we cannot help but dream of another solution, a hidden door through which we might slip to find ourselves somewhere new. Yet, as we stand there in the hush of night, the cosmos whispers possibilities. Perhaps these distances are not as unbridgeable as they seem. Perhaps, hidden in the fabric of space itself, there are secret tunnels or shortcuts threading their way between far-off corners of the universe. It sounds like pure fantasy, like something out of a dream. But the greatest wonders of reality often first appear as mere whispers in our dreams, don't they? And so, we allow ourselves to imagine. Imagine a path that could take you from here to a star on the other side of the galaxy in an instant. A gentle tunnel through which you might step and find yourself someplace impossibly far away. No rocket required, no decades spent drifting in the void. Just one step, and you're there. What a beautiful idea. A cosmic shortcut, a hidden bridge connecting distant points of the universe. For ages, humans have felt the allure of such ideas. Long before we had science to explain the heavens, we filled the night sky with stories. We spoke of gods and monsters living among the stars, of heavenly roads and mystical doorways to other realms. Those were the earliest whispers of a yearning, to find pathways where none were obvious, to believe that the great distances might somehow be crossed in the blink of an eye. Tonight, under the stars, that ancient yearning feels as alive as ever. Perhaps it's the quiet that brings these thoughts to the surface. In the stillness, our minds can roam free, dancing among the stars, daring to imagine the impossible. And in that act of imagination, in that gentle wondering, there is a kind of magic. The universe encourages us with its silence, inviting our questions. Could it be that somewhere in the vast tapestry of space, there are hidden doorways waiting to be found? We have no evidence of them yet. No photograph of a glowing cosmic doorway. No map leading us through a secret tunnel in space. But the idea itself is like a soft light glimmering at the edges of our understanding. An idea so compelling that it refuses to fade away. Scientists and dreamers alike have heard this whisper. Some have devoted their lives to teasing it apart, to seeing if there's truth within it. Standing here, feeling the cool night air and gazing at eternity above, it's easy to feel that anything is possible. The stars do not tell us their secrets outright, but they inspire us to seek. Every so often, a shooting star streaks by, a brief, startling flash. It's a reminder that even against the backdrop of eternity, there are moments of wonder and surprise. And perhaps those surprises include the discovery of something extraordinary, a hidden pathway among those stars, a tunnel through space and time. So, we listen to the cosmos with open hearts and curious minds. We listen to its whisper of hidden pathways and impossible journeys. The journey we're about to take is one of imagination, grounded in science. A gentle expedition through ideas at the very frontier of what we know. It begins with understanding the very stage upon which this cosmic drama unfolds. The fabric that underlies everything. The invisible scaffold of reality itself. The cosmos's whisper grows quieter now, guiding our attention inward, toward the fundamental nature of space and time. To follow the hint of those secret tunnels, we first need to understand the material of the tapestry we might tunnel through. And so, our journey leads us to ponder the nature of space-time, the silent, invisible fabric stretching beneath all things, carrying the weight of stars and the dreams of those who gaze upon them. To follow the whisper of hidden cosmic pathways, we must first understand the stage on which all cosmic journeys take place. Imagine for a moment that everything in the universe, every planet, every star, every mote of dust, and even you and I, is resting on a vast, invisible blanket. This blanket stretches out in all directions, unending and unseen. We call this blanket space-time. It isn't a fabric we can touch or see, yet it's very real. Space-time is the very framework of reality, the combination of space and time woven together into something like a fabric that underlies everything. For centuries, people thought of space and time as separate things. Space was just the empty room in which things happened, and time was like a steady drumbeat that ticked away in the background, the same for everyone everywhere. But in the early 20th century, a brilliant change in perspective occurred. Scientists came to realize that space and time are deeply connected. They aren't separate backdrops at all. They are two parts of one whole. One mathematician, reflecting on this discovery, said that from that moment on, space by itself and time by itself would fade into mere shadows, and only a kind of union of the two would preserve an independent reality. In simpler terms, from now on, we need to think of space and time as one thing: space-time. This idea might feel a bit abstract. How can time and space be the same thing? Think of it this way. When you want to meet a friend, you give them not just a place, but a time as well. Let's meet at the park at 3 p.m. The park is the space, 3 p.m. is the time. Both are needed to define the event of your meeting. In a sense, the event has coordinates in space-time, a location and a moment. Without the time, the where is incomplete. Without the place, the when is incomplete. In our everyday life, we sense that space and time are intertwined because every happening is pinned to both a place and a time. Space-time goes even further than that simple example. According to Albert Einstein's theories, space and time aren't just abstract labels we assign to events. They form a connected fabric that can be stretched, compressed, and even twisted. If you move very fast, for instance, time itself will pass differently for you than for someone who is standing still. This isn't just a wild guess, it's a measured fact. A clock on a fast-moving spaceship will tick slightly slower compared to a clock on Earth. And a clock high up on a mountain, where gravity is a tiny bit weaker, ticks a bit faster than one at sea level. These strange truths revealed that time can stretch and shrink, much like space can. It was a sign that time and space are woven together deeply, affecting one another. So, space-time is essentially the arena of the universe. It has 4 dimensions, 3 dimensions of space, length, width, height, and 1 of time. We can't visualize 4 dimensions directly, but we can imagine a 3-dimensional grid extending around us to represent space, and then imagine time as another dimension that we move through. Every object, every person, every planet is moving through both space and time simultaneously, always. In fact, right now, you are not just sitting or standing where you are. You're also moving steadily into the future, second by second. That movement through time is as real as your movement through space, and both together trace your path in space-time. Now, although we call space-time a fabric or blanket to help imagine it, it's not a material like cloth. These are metaphors to get our intuition involved. But the idea of it being able to stretch or bend is very true. Space-time can be warped and curved by objects and energy. Even though we can't see space-time directly, we can see what happens when it curves. Imagine again that invisible blanket spread out under everything. If the blanket were perfectly smooth and nothing was on it, an object placed on one side would just sit there. And if you had another object, it could slide in a straight line without anything unusual happening. This is like space-time without any mass or energy in it. Flat and uncurved, the simplest kind of space-time. But the universe is not empty and smooth. It's filled with objects both giant and tiny. And when you place something on our imaginary blanket, say, a heavy ball, the blanket will sag or dent around that weight. This is a way to picture what a massive object like a star or a planet does to space-time. It causes a dent or a curve. If another smaller ball comes rolling by, it won't continue in a straight line. Instead, it will be drawn into the dent, maybe even orbit around the heavy ball, the way Earth orbits the Sun. We often say the Sun's gravity keeps the Earth in orbit, but another way to picture it is that the Sun's presence has curved space-time around it, and Earth is rolling along that curve, unable to go straight. This new way of seeing things was a revelation. Gravity, which we used to think of as a mysterious force pulling objects across empty space, can be understood as objects following the curves and slopes in the space-time fabric. Massive things like stars and planets create valleys and dips in space-time, and other objects move accordingly, as if pulled by an unseen string, when really they are just gliding along the curves that are there. Understanding space-time as this dynamic, shapeable fabric is key to our journey. Because if we're going to talk about hidden tunnels and shortcuts through the cosmos, those tunnels would be bored through this very fabric. It's like realizing that if you can bend the fabric, maybe you can also fold it or connect distant points on it. We're not there yet, but we're preparing the ground. We now have a sense of what this invisible stage, the backdrop for all stars, planets, and ourselves, is really like. Flexible and responsive, a fabric that can ripple, bend, and perhaps, just perhaps, form bridges. We've come to see space-time as something alive with possibilities. It can stretch slowly as the universe expands. It can ripple when stars collide far off in the darkness. In fact, not long ago, we managed to listen to those ripples with sensitive instruments on Earth. When two massive black holes crashed into each other in a far-off galaxy, the very fabric of space-time vibrated from the impact, and we detected that faint vibration. It was as if we heard the universe whisper through those cosmic ripples, confirming that this invisible fabric can indeed carry soundless echoes of distant events. Space-time can curve gently or steeply around each object that has mass. In this understanding lies the hint of something profound. If space-time can be curved by mass, could it be curved or manipulated in such a way that two distant points might touch? Like folding a blanket so that two far corners come together, might there be a way within Einstein's cosmic fabric to bring far-flung places side by side? This is where our journey naturally flows next. Having glimpsed space-time as the pliable fabric under the cosmos, we turn to Einstein's great insight about how that fabric bends and what that means for gravity. In uncovering how gravity really works, we'll come even closer to understanding how a shortcut through space and time might be possible. The fabric is laid out before us. Now we watch as it curves under the weight of reality, guiding us toward the next step in unraveling the mystery of cosmic tunnels. Gravity was once a riddle wrapped in everyday life. We feel it when our feet press against the ground, when apples fall from trees, when planets tug on each other across the solar system. For a long time, we explained this as a kind of invisible pull that masses exert on one another. Isaac Newton imagined gravity as a force acting at a distance, a mysterious hand reaching across space. His law of gravity, formulated in the 17th century, described the motions of planets and the fall of apples with astonishing accuracy. But even Newton admitted he didn't know how this invisible force worked, only that it did. The puzzle of gravity's true nature lingered in the background, quietly waiting for a new insight. Albert Einstein provided that new insight in 1915, fundamentally reshaping our concept of gravity with his general theory of relativity. The road to this breakthrough was paved with imaginative leaps as well as rigorous calculations. At one point, Einstein experienced what he later called the happiest thought of his life. He imagined a man falling from the roof of a house and realized that during the fall, the man would feel weightless, as if gravity had vanished. In that simple mental picture, Einstein sensed a profound truth. Being pulled by gravity and freely falling are really the same experience. This clue suggested that gravity might not be a mysterious force reaching across space, but rather something arising from the shape of space and time itself. It took Einstein years of work to turn this clue into a precise theory. But when he finally succeeded in 1915, the result was astonishing. He had shown that gravity wasn't a mysterious pull acting at a distance, but the natural result of space-time's shape. Matter told space-time how to curve, and space-time in turn told matter how to move. What we feel as gravity is really objects sliding along the curves and slopes in the space-time fabric. It was a completely new way to understand why the moon circles the Earth and why an apple falls from a tree. No forces reaching across empty space, just the subtle guidance of curved space and time. At first, this idea sounded strange, even to other scientists. Space curved? Time altered by mass? It was a leap away from the intuitive, clockwork universe everyone thought they lived in. But the beauty of Einstein's theory was that it could be tested, and nature soon revealed that Einstein was right. One early triumph of general relativity came from the tiny planet Mercury. For decades, astronomers had been puzzled by Mercury's orbit. It didn't trace the same path over and over. Instead, the point of its closest approach to the Sun drifted slightly with each orbit. Newton's theory couldn't fully explain this wobble. Einstein's theory did. When he calculated Mercury's orbit using space-time curvature, the discrepancy vanished. The drift was exactly accounted for. It was a quiet victory, one that hinted at the power of this new understanding. An even more dramatic test came in 1919, during a total eclipse of the Sun. On that day, the moon slid in front of the Sun, blocking its blinding light and allowing the stars near the Sun to be observed in the daytime sky. During this brief darkness, astronomers took photographs of the star field around the eclipsed Sun. Later, when they compared those images to pictures of the same region of sky taken at night, they found something extraordinary. The stars' positions had shifted, ever so slightly. The starlight had passed close by the Sun and had been bent by the curved space-time around it, just as Einstein's equations predicted. When the world heard of this result, Einstein's strange new theory suddenly felt very real. The headlines declared that gravity had indeed bent starlight, and in doing so, had confirmed that the universe itself could bend and stretch. With each success, Einstein's curved reality became the accepted reality. We learned that we live in a pliable universe, one where space can warp and time can shift. Gravity was revealed not as a pull, but as a path that mass creates through the fabric of space-time. And as we came to accept this, our imaginations began to stretch along with our science. If space and time could bend into curves, might they fold over entirely? Could two distant points, separated by light years, ever be brought together, perhaps even touch? These questions sound fanciful, but the new shape of gravity made people wonder in ways they hadn't before. Think of space-time like a great canvas that can be deformed. A heavy object makes a dip. A rotating object can even twist that canvas slightly, dragging space and time around with it. In extreme cases, Einstein's equations hinted at even stranger possibilities. For example, if enough mass were concentrated in a small enough volume, space-time could curve so steeply that it essentially pinches off. It was the theoretical idea of a bottomless pit in the fabric of the universe, a concept later dubbed a black hole. In fact, only months after Einstein published his theory, a physicist named Carl Schwarzschild discovered such a solution lurking in the equations. It described a point of almost infinite density, wrapped in a region from which nothing could escape. Einstein was intrigued, but not convinced nature would create such an extreme object. Now, a century later, we have strong evidence that black holes are real, lurking out there in the darkness. One more affirmation of how far Einstein's curved reality can go. If such extreme distortions as black holes can exist, might nature allow other exotic shapes in the fabric of space-time? Imagine something akin to a tunnel. Not a well with a dead end, but a passage leading elsewhere. Einstein's theory didn't rule this out. In fact, the mathematics of general relativity are so rich that they permit solutions which look like bridges or tunnels connecting different points in space and time. These solutions wouldn't be common. They might require unusual conditions, but the possibility was there, glimmering in the equations, and it sparked curiosity. Einstein himself, along with other pioneering thinkers, noticed these odd possibilities peeking out from the mathematics. They were intrigued by the idea, though at first it remained a theoretical curiosity, a strange quirk of the equations more than anything concrete. Still, the seed was planted. Hidden within Einstein's own theory was the hint of a shortcut through space and time. It wouldn't be too long before this idea gained a name and a life of its own. It's here that science fiction and science fact start to touch. As soon as Einstein gave us a universe that could bend and warp, creative minds in both physics and literature began to play with the implications. The idea of cosmic shortcuts, once merely fantasy, gained a foothold in scientific plausibility. If gravity could bend a beam of light across space, perhaps, just maybe, space could bend enough to let that beam emerge somewhere else entirely, through a hidden corridor in space-time. This notion, that the universe might contain hidden doorways or bridges, began to take root. At this stage, it was still only a speculative glimmer, without a formal name, but it was growing clearer in both science and storytelling. Before we dive into the formal scientific proposals for such tunnels, it's worth pausing to appreciate how the idea took hold in the human mind. The early 20th century was a time of both scientific breakthroughs and wild imagination. Einstein's work bent the universe in our minds, and into that new, curved space rushed all sorts of dreams about what might be possible. And so, with space-time now understood as dynamic and malleable, the stage was set. Our next steps would explore those early dreams of cosmic shortcuts, dreams that flickered to life in the wake of Einstein's revelation. In the quiet spaces between solid facts and speculative wonder, humanity began to imagine the impossible more vividly than ever. Let's follow those imaginings now, tracing how the concept of shortcuts through space, once a mere whisper in the dark, started to become a topic of serious thought and adventurous storytelling alike. Before scientists formally described tunnels through space and time, the idea had already taken root in the human imagination. In fact, it's fair to say that the dream of cosmic shortcuts is ancient, born from the same yearning that made our ancestors tell stories of magical doorways and enchanted paths. Long ago, people imagined portals to realms beyond the ordinary, a mirror that one could step through into a wonderland, a wardrobe that opened upon a distant world, a bridge made of rainbow light leading to the land of gods. These early legends and fantasies weren't about physics, but they spoke to a deep hope that perhaps the vast distances and barriers of our world could be bypassed if only one knew the secret route. As our understanding of the universe grew, and we realized the stars were suns like our own, separated by unimaginable gulfs of space, that old yearning for shortcuts only intensified. By the late 19th and early 20th centuries, writers and dreamers began to contemplate what science might offer to fulfill those dreams. The concept of hidden dimensions beyond the familiar three began to surface in both mathematics and fiction. If a higher dimension existed, maybe it could provide a backdoor between far apart places. The notion was intoxicating. Just as a hole drilled through a mountain can spare travelers a long journey over winding roads, perhaps a tunnel through an unseen fourth dimension could spare travelers a journey across light years. Early science fiction writers eagerly embraced these ideas. At a time when a voyage to the moon was still only a fantasy, they were already imagining voyages to distant stars by unconventional means. Some wrote of space warps and hyperspace, mysterious shortcuts that could whisk a spaceship from one star system to another in an instant. In their stories, explorers would activate a device or utter a secret formula, and a doorway would open in the void. Step through it, and you might emerge on the other side of the galaxy. These tales appeared in pulp magazines with vivid illustrations, perhaps a shining tunnel stretching between star clusters, or a cosmic doorway swirling with light. The details varied wildly from one story to the next, but the core idea was the same. There must be a quicker way to traverse the vastness of space than mere rockets or light-speed travel. In imagination, if not yet in reality, the universe began to feel a bit smaller and more connected. Even within the scientific community, there were those willing to speculate beyond the known. After Einstein's theories reshaped space and time, a few scientists wondered aloud whether general relativity might allow some form of shortcut. These were informal musings, thoughts shared perhaps over letters or late-night conversations. Most mainstream science stayed cautious and focused on what could be observed and measured. But the what-if questions quietly persisted. What if space-time could fold over on itself, bringing two far points together? What if a tunnel could form, bridging two corners of the cosmos? Such ideas were far from proven, but they tickled at the edges of what scientists felt might be possible someday, under the right circumstances. Meanwhile, the popular imagination raced ahead. Newspapers and magazines occasionally ran whimsical pieces about ideas on the fringe of science. One might read an article musing about travel through the fifth dimension, or a fanciful interview with a physicist speculating on future interstellar travel. These were glimpses of a culture beginning to flirt with the outrageous possibilities that relativity hinted at. Often, the science was stretched thin in these accounts, but that hardly mattered. What they offered was inspiration, a sense of wonder that perhaps one day we really might slip through a crack in space and find ourselves somewhere far, far away. In literature and early cinema, the theme of hidden passageways blossomed. Characters found secret doors in ancient temples that led to alien worlds. Scientists in stories would invent miraculous machines to teleport themselves to Mars or beyond. Audiences of the time, living through an era of rapid technological progress, were primed to believe that almost anything was possible. The airplane had conquered the sky. The radio had conquered distance in communication. So why not believe that some invention might one day conquer distance in space outright? If a rocket could not practically reach the nearest star within a human lifetime, maybe a different approach, a clever trick with space and time, could make it feasible. One beautiful aspect of these early dreams is how they blended mysticism and rationality. Writers would invoke the latest scientific theories, like Einstein's curved space, or the existence of dimensions beyond the third, and then weave them together with age-old imaginative tropes of gateways and shortcuts. The result was a kind of modern myth-making, wormholes before they were called wormholes, cast in the form of story and metaphor. In these stories, you can sense both the excitement of new science and the enduring human desire for connection and discovery. Consider, for example, the idea of a door in the sky. A character gazes up at a star and wonders, what if I could walk through a door and be there? Science fiction gave shape to that question. Some tales described pilots flying into strange clouds or magnetic storms and unexpectedly emerging in completely different star systems, an adventurous twist on the concept of a cosmic tunnel. Others imagined stable gateways constructed by ancient civilizations, waiting to be found and activated. Step through such a gate, and you might step onto an alien shore under a different sun. These were flights of fancy, but not entirely detached from reality. They often drew from whatever scientific knowledge was available, then leapt further. And as fanciful as they were, they helped prepare the public imagination for what science might eventually discover. By dreaming about cosmic shortcuts, people were, in a way, practicing for the day when such shortcuts could be discussed in serious scientific terms. Of course, not everyone entertained such ideas. Many scientists and thinkers were skeptical, and rightly so. No evidence of any space-time tunnel existed, nor any known way to create one. To many, these remained purely hypothetical, confined to chalkboard equations or science fiction plots. But important ideas often start on the fringes, whispered about before they move towards center stage. The early dreams of cosmic shortcuts were like a collective thought experiment, one that spanned decades and bridged the gap between creative storytelling and theoretical physics. By the early 1930s, the world had heard of Einstein's relativity and the strange warping of space-time it entailed. The term black hole had not yet been coined, and wormhole was still years away from being named, but the intellectual soil was being tilled. Imaginative minds had planted seeds in that soil, seeds of curiosity and possibility. So when the first serious scientific paper on a space-time tunnel appeared mid-century, the ground was, in a sense, ready. People had been speculating and dreaming about such things for years. Those early musings and fantastical stories formed a bridge of their own, a bridge from pure fantasy towards scientific inquiry. They kept alive the question, could there be a shortcut? They made it easier for the scientists who came next to take the idea seriously, or at least not dismiss it outright. In the quiet turning of pages and the hushed conversations of late-night stargazers, the impossible was imagined over and over, until it started to feel just a little more plausible. Now, as we leave these early dreams and return to the path of science, we find ourselves on the threshold of the Wormholes' formal debut. With the stage set by both imagination and theory, the time was ripe for someone to tie it all together. And indeed, that moment came when Einstein, together with a collaborator, decided to peer into the mathematical underpinnings of gravity once more. In doing so, they would bring the whisper of cosmic shortcuts into the light of scientific discourse, giving us the first glimpse of a wormhole in the language of physics. Our journey continues to that pivotal moment, the birth of the Einstein-Rosen bridge. In the mid-1930s, beneath the quiet trees of Princeton, Albert Einstein was hard at work once again, delving into the equations of gravity that he had formulated 2 decades earlier. By his side was a young colleague named Nathan Rosen. Together, they were exploring some deep puzzles of the theory of general relativity, searching for insights into the nature of particles and gravity. It was during this exploration that they stumbled upon something remarkable in the mathematics, a solution that looked like a bridge between 2 worlds. What Einstein and Rosen found was that the equations of gravity allowed space-time to form a kind of tunnel. In their 1935 paper, they described what came to be known as the Einstein-Rosen bridge. To envision it, imagine space-time as a vast sheet that can be bent and curved. Now picture 2 distant regions on that sheet. They could be 2 far apart places in our universe, or even 2 separate universes altogether. The Einstein-Rosen solution suggested that it was possible, at least in theory, for a tunnel to exist that connects those 2 regions directly, like a secret passageway through the fabric of space and time. A helpful analogy is to picture 2 bowls placed rim to rim. Each bowl represents a deep gravitational well, essentially a black hole, a place where space funnels down toward a center. Where the insides of the two bowls touch, a tunnel forms. One bowl's interior leads into the others. In the Einstein-Rosen bridge, one end of the tunnel could be seen as a black hole, an entrance where things could fall in, and the other end could be interpreted as an exit, sometimes imagined as a kind of white hole where things might come out. In essence, their mathematics showed a complete pathway through space-time. Fall into one black hole, and if conditions were just right, you might emerge out the other side. Einstein and Rosen were not science fiction writers. They approached this idea with caution and mathematical curiosity. In their view, this bridge wasn't conceived as a cosmic subway for spacecraft or people. They were wrestling with theoretical questions, trying to eliminate what they saw as troublesome infinities, the singularities inside black holes, and to perhaps model fundamental particles as tiny bridges in space. The Einstein-Rosen bridge was a byproduct of these investigations, a surprising and elegant solution that suggested two regions of space could be connected by a short tunnel, even though those regions might be very far apart, in the normal sense. At the time, this idea was as strange as anything could be. Remember, in the 1930s, even the idea of black holes was speculative. The term black hole itself hadn't been coined yet. Scientists of the day spoke of collapsed stars or other cautious descriptions. To propose a bridge through a black hole to another space was pushing into truly exotic territory. Einstein, with his renowned intuition, understood the mathematics, but he remained skeptical of whether such a tunnel would have physical meaning. The Einstein-Rosen paper treated the bridge as a fascinating mathematical artifact, one that might avoid the notion of an infinitely dense point at the center of a black hole. It wasn't presented as a method of travel or a practical shortcut. In fact, the paper doesn't describe anything going through the tunnel at all. It was more about the structure of space-time itself and what it might allow in principle. Nevertheless, the concept had an undeniable allure. Here was a legitimate solution of Einstein's gravitational field equations, hinting that space-time might be more interconnected than we ever imagined. It suggested that the universe could have hidden handles or tunnels threading through it. Einstein and Rosen's work implied that if one fell into a certain black hole under just the right conditions, instead of being lost forever, one might pop out somewhere else, as if the black hole were a door to another place, rather than a dead-end sinkhole. In the years immediately after this revelation, the Einstein-Rosen bridge largely remained a mathematical curiosity. World events were tumultuous. The late 1930s and 1940s saw the outbreak of World War II, and physics had its hands full with more tangible concerns like nuclear energy. The bridge idea, while published in a respected journal, did not immediately transform into front-page news or spawn a line of experiments. It lived quietly in the pages of theoretical physics, waiting for the right time and the right minds to delve deeper. One reason for this quiet reception was that, as beautiful as the Einstein-Rosen bridge was on paper, it had issues that were hard to ignore. Other physicists who studied it realized that the bridge was incredibly unstable. If you tried to travel through it, even as a beam of light, the tunnel would pinch shut almost as quickly as it formed. It was like a soap bubble that pops the instant you touch it. In essence, nature seemed to protect its cosmic distances with a kind of fail-safe. This first wormhole was not traversable, meaning nothing could actually go from one end to the other before the passage collapsed. Einstein himself, true to his cautious nature, suspected that real-world physics would prevent such shortcuts from being usable. And so, for a time, the Einstein-Rosen bridge remained a sort of theoretical footnote. Fascinating, yes, but not something you could base a spaceship itinerary on. Still, the seed had been planted in fertile ground. Other scientists, especially in the decades that followed, would remember that seed and wonder if it could possibly grow into something more robust. The term wormhole had not yet been coined. That would come later, in the 1950s, courtesy of physicist John Wheeler, who imagined these tunnels and whimsically named them after the holes worms bore in apples. But even without the catchy name, the Einstein-Rosen bridge was essentially the first wormhole acknowledged by science. It marked the beginning of a new chapter in our thinking about space and time. The universe, as described by Einstein's relativity, had offered up a startling possibility: a tunnel through the cosmic fabric. It was as if a door had been glimpsed, if only just barely cracked open, in the vast wall of space separating stars and galaxies. For now, that door appeared to slam shut the moment anything tried to pass through. But the mere glimpse of it was enough to inspire generations of physicists to ask, what if we could keep it open? What would it take to travel through a wormhole? And if one could travel through such a tunnel, what astounding things might be possible? Perhaps even journeys through time itself. Einstein and Rosen's pioneering work left us with profound questions rather than answers. It hinted that the wild dreams of shortcut pathways might not be pure fantasy after all. They might be embedded in the mathematics of reality, albeit with significant caveats. The first bridge had been found, but it was a rickety one, flickering in and out of existence within the equations. The task ahead, for the dreamers and thinkers who followed, would be to understand whether a more stable bridge could ever exist, or whether nature truly prohibits a free lunch when it comes to cosmic travel. As we pause here, at the end of this part of our journey, we find ourselves on a threshold. We have gone from ancient whispers and imaginative tales all the way to a serious scientific proposal for a tunnel through spacetime. The Einstein-Rosen bridge stands as a testament to human curiosity and creativity, born from equations, yet resonant with the age-old desire to find a shortcut to distant realms. Though Einstein's bridge was ephemeral, the idea of the wormhole had now stepped into the light of day. Our journey is not over. The story of wormholes is just beginning to unfold. In the chapters to come, we will see how this concept evolved, how it gained the name wormhole, and how physicists began tackling the challenges that Einstein's first bridge could not overcome. We will explore what it would take to hold a wormhole open, the strange requirement of exotic matter, and the tantalizing possibility that a wormhole, if it could be stabilized, might even allow us to travel through time. For now, we drift in the knowledge and wonder of this moment in history, the first glimpse of a tunnel through the stars, given to us by one of the greatest minds to ever gaze up at the cosmos. It's a hint that the universe may be far more connected and mysterious than it ever seemed, even in our wildest dreams. In the silent darkness between distant stars, one can imagine drifting upon something extraordinary. It would appear at first like a faint distortion, a ripple in the fabric of space. As you glide closer, this ripple resolves into what looks like a floating doorway, a gateway hanging in the cosmic void. This is a wormhole, a theoretical passageway between far-flung corners of the universe. It's an unseen door connecting stars, galaxies, or perhaps even different times, waiting quietly in the starlight. The scene is peaceful and eerie. Stars speckle the void in every direction, and nothing seems to break the stillness. Then, gradually, you notice that one patch of stars ahead looks slightly distorted. It's as if you were looking through a piece of curved glass. The starlight there is a touch warped, hazy at the edges. At first you might dismiss it as a trick of your eyes or an optical glitch, but as you drift closer, the distortion grows more pronounced, refusing to disappear. Something is indeed there, bending the view like a hidden lens in space. Your heart might skip a beat at the realization. This is no ordinary star or nebula, but possibly the signature of an unseen doorway. Up close, the doorway might not look like a flat door at all, but rather a dark, spherical opening. In many depictions, a wormhole would appear as a sphere suspended in space, like a window into another part of the cosmos. The view through it might not match the surrounding stars on this side. Perhaps you'd see the glow of a distant nebula or galaxy from the far end. Around the edges of the sphere, the light from behind could be stretched and distorted into a shimmering halo. This distortion, caused by the wormhole's intense gravity-bending light, would be a telltale sign that you have found an interstellar passageway. It's a sight both eerie and mesmerizing, a dark globe hanging in space, quietly holding a secret view of a far-off realm. From a distance, you might even mistake it for a black hole. Like a black hole, a wormhole's gravity could bend light and cast a shadowy, spherical silhouette. But unlike a true black hole, this strange sphere isn't a one-way trap. If you shine a beam of light at it just right, the light doesn't vanish. Instead, it emerges on the other side of the universe. A black hole would swallow light entirely, allowing nothing to escape once past its horizon. A wormhole, by contrast, has no event horizon sealing it. It is an open tunnel. With the proper trajectory, beams of light, or a spacecraft, could enter one end and come out the other. It's a critical difference that sets the wormhole apart. It looks dark and mysterious, yet it is, in theory, a doorway rather than a pit. If you were to drift around this sphere, the view through it would change in bewildering ways. From one angle, you might see straight through to the other side of the universe, a patch of sky filled with unfamiliar stars or swirling clouds of cosmic dust. But as you move to the side, the wormhole becomes like a cosmic funhouse mirror. Light skims the edges of the spherical doorway and bends sharply, warping the appearance of whatever lies behind it. Stars and galaxies might stretch into arcs of light around the portal, a halo marking the boundary between ordinary space and the tunnel beyond. Astronomers have a name for the kind of warped halo you might see: an Einstein ring. It's a phenomenon usually associated with massive objects like black holes or galaxies bending the light of more distant stars into a circle. A traversable wormhole could produce a similar effect. If you were positioned just right, you might see the light from whatever lies beyond the wormhole smeared into a ring around the dark sphere. It would be as though the edges of the portal are traced by a halo of distorted starlight, a glowing outline sketching the mouth of the tunnel. This gravitational lensing would be a cosmic calling card of the wormhole's presence, a subtle cue that space is bending in an extraordinary way at that spot. Light skims the boundary and turns, revealing the portal by its bending of the starry backdrop. If you orbit around, you witness different patterns of distortion. The effect is both beautiful and disorienting, as though space itself is whispering that something extraordinary is here. To witness stars and nebulas contort around an invisible boundary is to feel the strange pull of the unknown, equal parts wonder and apprehension. Despite these distortions, a wormhole itself might emit no light of its own. If the far side of the wormhole opened into the black void of deep space, the portal could be almost impossible to spot without a keen eye. It would be as if an empty sphere were hanging there, detectable only by how it bends the starlight behind it. In many science fiction tales, Wormholes are shown as luminous tunnels or swirling vortices. Reality would likely be more subtle, a silent gateway marked mainly by a gravitational mirage. Only when you come very close or peer at just the right angle would the doorway reveal itself, showing a glimpse of whatever lies on the other side of space and time. A wormhole could lurk silently in the void, virtually undetectable except to the most discerning eye or instruments that notice its ghostly gravitational footprint. What would it feel like to step through such a cosmic door? If you dared to cross the threshold, you might not experience a long journey at all. One instant you're at the entrance, and the next you're expelled out the other side, light years away. Some imagine a tunnel of swirling light, as if you're shooting through a luminous vortex. Perhaps inside the wormhole, space warps so strangely that you could even see the back of your own spaceship, light curving around in the tunnel. Or maybe the transit would be eerily quiet and dark, a brief nothingness before a new sky appears. Nobody truly knows, because no one has ever seen the inside of a wormhole. For now, it lives in our imagination and in the equations of physics, teasing us with possibilities. The very idea of stepping through such a portal can send a shiver down one's spine, a mixture of exhilaration at the possibility and fear of the unknown. The physics inside a wormhole could be mind-bending in the literal sense. Some scientists have mused that if you were deep in the tunnel and glanced sideways, the curvature of space might allow you to see the back of your own head. Light could loop around the tunnel and return to your eyes, offering a surreal, Escher-like view of yourself. It's a strange thought, essentially looking into a cosmic mirror formed by the wormhole's curved geometry. Such speculation captures how bizarre the wormhole environment might be, warping perception along with space and time. In a very real way, traversing a wormhole could mean stepping into a realm where normal rules of sight and distance break down completely. Because wormholes are so hard to visualize, scientists and educators often turn to analogies. One famous analogy is to imagine space itself as a sheet of paper. Normally, traveling from one point on the paper to another means moving across the sheet. But if you fold the paper so that two distant points touch, suddenly there is a shortcut, a tunnel through the paper that connects those points directly. A wormhole is just like that, but with the fabric of space-time. It's as if the universe can fold over and offer a secret bridge, letting you step across vast distances in a single leap. This folding trick suggests that wormholes may involve dimensions beyond our everyday three. In the paper analogy, we had to lift the 2D sheet into a third dimension to make the shortcut. Likewise, a real wormhole might require bending our 3D space through a fourth spatial dimension, or some structure of space-time we can't directly see. It's a difficult concept. We humans can't truly visualize four-dimensional space, but the math of general relativity allows such higher dimensional warping. Essentially, a wormhole could be a bridge that cuts through the fabric of space-time in an unseen direction, connecting two distant spots in our normal space. That idea is as hard to grasp as it sounds, which is why simple analogies like folded paper are so helpful. The very name wormhole comes from another analogy. Picture a tiny worm crawling on the skin of an apple. For the worm, the apple's surface is like the universe, a two-dimensional world it must crawl across. If the worm wants to reach a point on the opposite side of the apple, it could creep over the curved surface, a long journey around. Or it could chew straight through the apple and emerge on the other side. That little tunnel through the apple is the worm's shortcut, a wormhole. In the same way, a wormhole in space-time is a shortcut through the cosmic apple of our universe, a tunnel that bypasses the long trek through normal space. It's a homely image that turns an abstract idea into something almost tangible, a reminder that sometimes a clever shortcut can exist where none seemed possible. As vivid as these mental pictures are, they remain speculative. To date, no telescope or experiment has caught a glimpse of a real wormhole. They live in the realm of theory, supported by Einstein's equations, but not yet by any evidence. Still, visualizing these unseen doorways helps us grasp what might be possible. It stirs the imagination and pushes physics into uncharted territory. But imagining a wormhole is one thing. Making or finding one is another entirely. How could such a passageway be kept open? What kind of cosmic machinery would be required to stop a wormhole from collapsing and allow travelers or messages through? The next step in our journey explores the strange answer scientists have proposed. A source of energy so exotic that it might as well be impossible. To turn these imagined doorways into reality, we would have to satisfy some extreme requirements of physics, demands so outlandish that they strain credibility. This is the puzzle we face next. By all ordinary laws of physics, a wormhole's tunnel would snap shut almost as soon as it formed. Gravity, the same force that makes planets and stars round, would pinch the throat of the wormhole closed. To hold a wormhole open, something extraordinary is required. A kind of matter with gravitational properties unlike anything we've ever seen. Scientists call it exotic matter. Unlike normal matter, which has positive mass and pulls things together, exotic matter would have negative energy and mass. It would push space apart. In theory, lining a wormhole with a shell of exotic matter could keep the passageway propped open, preventing gravity from crushing it closed. It would act as a kind of anti-gravity scaffold. Exotic matter is not just rare, it's something we aren't even sure nature allows in any significant amount. In our everyday experience, mass is always positive, and gravity always attracts. Negative mass or negative energy sounds almost like a fairy tale. It suggests matter that would fall upward or cause surrounding objects to repel. Such properties have never been observed in any object or particle. In all our experiments and observations, every particle and object we've encountered obeys the rule of positive mass, attracting other matter through gravity. The concept of something with weight that pushes instead of pulls remains a purely theoretical fancy. Exotic matter, if it exists, would break all the normal rules. If a rock made of exotic matter sat on the ground, it might actually float upward because gravity would push it away. We've never seen anything like that. In all of physics so far, negative mass is an idea that lives only in theory. There are slight hints that negative energy can exist in nature, but only in tiny, fleeting ways. Quantum physics predicts that even a perfect vacuum isn't truly empty. Virtual particles flicker in and out of existence. In special setups like the Casimir effect, physicists have measured a small force that implies a region of space has a lower energy than normal empty space, effectively a tiny bit of negative energy. The Casimir effect arises when two metal plates are placed extremely close together. Certain vacuum energy modes are suppressed between them, creating a pressure that pushes the plates together. But this phenomenon is incredibly delicate and only noticeable on subatomic scales. The amount of negative energy generated is exceedingly small, far too minuscule to hold open anything as grand as a wormhole. No one has ever created a lump of stable, negative mass matter that we could hold in our hands or build with. The exotic matter needed to stabilize a wormhole remains purely hypothetical, a speculative requirement that might not exist at all. For now, Exotic matter exists only in the pages of theoretical physics papers and the imaginations of scientists, a signpost that our wormhole ambitions demand physics beyond our current grasp. Interestingly, our universe may already contain something akin to a mild, diffuse form of repulsive gravity, the mysterious dark energy that is causing the expansion of the universe to accelerate. Dark energy isn't the same as the exotic matter needed for a wormhole. It's spread thinly throughout space and can't be bottled up or shaped into a tunnel wall. But its existence shows that nature does allow energy conditions that defy normal gravitational rules. Dark energy acts sort of like a uniform negative pressure permeating the cosmos, pushing galaxies apart. Unfortunately, dark energy is far too weak and diffuse to hold open a wormhole. It's more like a gentle pressure filling the universe than a structural support we could use. We can't grab dark energy and build with it. It's everywhere and nowhere, extremely faint. To stabilize a wormhole, we'd need something far more concentrated and controllable, a kind of super intense localized anti-gravity substance. And that remains purely hypothetical. Still, the presence of dark energy is a reminder that the cosmos does contain odd phenomena that break our intuitive rules. It hints that negative or repulsive aspects of gravity exist in our universe, even if they're not in a form we can harness for travel. Even if, by some miracle, we could obtain some exotic matter, the amount required would be staggering. The price of a wormhole, in terms of energy, is beyond anything humanity has ever handled. Rough estimates suggest that to hold open even a modest wormhole mouth, you'd need a quantity of negative energy comparable to the mass of a planet. In other words, a tiny wormhole might demand an exotic energy source equivalent to converting an entire world into a strange form of anti-gravity fuel. Physicists have estimated that to keep open a wormhole mouth only a meter or two across, one might need negative energy on the order of the mass of Jupiter. Imagine an entire gas giant planet's worth of matter, more than 300 Earths, but with a gravitational effect opposite to normal matter. And that enormous requirement would only hold open a doorway barely big enough to peek through. If you wanted a comfortably large, stable wormhole that a spaceship or person could travel through, the energy needs would soar into truly cosmic territory. One theoretical assessment suggested a human-friendly wormhole with gentle gravity inside so you're not ripped apart might require exotic matter equivalent to 100 million suns. It sounds absurd, and it is. Such figures border on the fantastical, even for the imagination of advanced galactic civilizations. It's as if nature set the price of admission to wormhole travel at a level no one can pay. Not humans, and perhaps not even any advanced species we can conceive of. In essence, the toll for a wormhole is quoted in cosmic terms. An energy budget drawn from stars and planets, far beyond any machine or technology we possess. These mind-boggling numbers firmly place traversable wormholes in the category of nearly impossible with our current understanding. For perspective, the mass of Jupiter is roughly 1,000th that of our Sun, an enormous amount of mass. To collect that in any form, let alone in an exotic form that repels gravity, is beyond imagining. It's the kind of requirement that makes even the most optimistic futurist shake their head. To say it's impractical is a vast understatement. Not even the combined output of all civilizations on Earth, or even the energy of a star, comes anywhere close to what's needed. It's a requirement so far-fetched that it verges on the absurd. All this underscores how daunting the wormhole concept truly is. Not just a step beyond our present capabilities, but a leap into an almost inconceivable realm of energy and matter manipulation. The numbers effectively act as a keep-out sign on these cosmic doorways. It's a sobering conclusion. Nature may permit wormholes in theory, but it doesn't seem to make them easy. That hasn't stopped scientists from playing with ideas. How might an advanced civilization bypass the impossible energy toll? One proposal, suggested by physicists Kip Thorne and his colleagues, involves taking a tiny wormhole, perhaps one that pops out of the wild fluctuations of space at the quantum scale, and then somehow inflating it to usable size. They imagined using huge electromagnetic fields or other forms of energy to hold the wormhole's mouth open. For example, by placing immensely powerful like-charged spheres at each end of a wormhole, one might use their electrical repulsion to counteract the hole's natural collapse. It's a bit like bracing open the jaws of spacetime with pillars of energy. The sphere's charges push outward on space, balancing the tendency of gravity to pinch the wormhole shut. It's a wildly ambitious blueprint. The idea of snatching a tiny wormhole birthed in nature's quantum foam and nurturing it into a macroscopic tunnel that someone could actually travel through. Other exotic schemes have been imagined as well. Perhaps an incredibly strong magnetic field or a spinning ring of dense matter could serve as the scaffold. Some have even speculated about cosmic strings, hypothetical defects in space-time left over from the Big Bang, that might be threaded through a wormhole to stabilize it. We don't know if cosmic strings exist, but in theory, a string with negative mass, if such a thing were possible, could prop a wormhole open. It's like trying every trick in the physics book to hold that tunnel open. It's extremely speculative and sits at the edge of what our theories can handle. All such scenarios demand technologies and energies far beyond anything we possess. They exist on the fringe of physics, thought experiments that reveal just how steep the price of a wormhole might be. It's as though we're sketching out how one might attempt to build a fairy tale castle, knowing full well we don't have the magic to actually do it. For the time being, such scenarios remain in the realm of thought experiments, imaginative exercises that illuminate where the boundaries of known science lie. In the end, the exotic matter requirement makes traversable wormholes look almost fantastical. It's as if the universe has imposed a steep toll for these shortcuts, one that no known civilization could afford. Maybe there are hidden loopholes in physics that someday will lower the cost, or some unforeseen discovery that changes the game. But with what we know now, a wormhole that one could travel through demands a kind of magic, an exotic source of gravity-defying energy that remains beyond our reach. It's a sobering thought that even if wormholes are allowed by the laws of physics, they appear to sit so far beyond our reach as to be virtually impossible. Naturally, we can continue to dream and search for new physics, but we must acknowledge how monumental the challenge is. Yet, even if one day we found a way to pay that exorbitant price, another daunting set of problems would arise. Imagine we have our wormhole, propped open by some miracle of technology. How do we keep it stable and use it safely? Wormholes, if they exist, might be incredibly fragile. The slightest perturbation, a bit of matter, a gust of radiation, could upset the delicate balance and cause the whole tunnel to collapse. Nature seems inclined to slam these doors shut at the smallest provocation. We've propped open the lion's jaws, but we still have to step through without getting bitten. And indeed, even if one could conjure the means to open such a cosmic door, holding it stable and safe introduces its own set of daunting challenges. The brutal truth about wormholes is that nature would try to destroy them almost as soon as they form. When physicists first derived wormhole solutions to Einstein's equations, they found a discouraging result. A simple wormhole, like the Einstein-Rosen bridge, collapses faster than anything can traverse it. Left to its own devices, a wormhole will pinch closed in the blink of an eye, like a soap bubble popping moments after it forms. neither light nor spacecraft would have the time to get through. In essence, a naturally occurring wormhole would be like a tiny flash, a brief glitch in spacetime that immediately heals itself. It's as though the universe itself is quick to snuff out any unauthorized shortcut, sealing the breach in spacetime almost as soon as it opens. Now imagine somehow we manage to hold a wormhole open, perhaps by lining it with that elusive negative energy or some advanced force field. Even then, the wormhole might sit on a knife's edge of stability. The slightest disturbance could send it crashing shut in an instant. Every bit of normal matter or energy that enters a wormhole adds positive mass energy to the system, and that threatens the equilibrium keeping it open. It's like stepping onto a fragile suspension bridge. Too much weight, and the whole bridge gives way. If a spaceship, with all its mass, attempted to pass through, its very presence could overwhelm the negative pressure holding the wormhole open. The tunnel might then collapse abruptly, crushing or stranding the ship in the process. Even a strong beam of light or a surge of radiation pouring through might destabilize the passage. The exotic matter scaffolding has to repel gravity just enough to hold the tunnel open, but if that repulsion is overwhelmed by incoming energy, the tunnel can close as violently as it opened. In effect, keeping a wormhole open might demand an almost impossible degree of control. Every stray particle, every beam of light would need to be accounted for, lest it tip the balance and send the tunnel crumbling. In such a scenario, using a wormhole would be akin to tiptoeing across a razor-thin bridge over a cosmic abyss. Any misstep could be disastrous. To truly grasp the danger, imagine what a collapsing wormhole would mean for a traveler. One moment, you are partway through this cosmic tunnel, seeing the light of a distant star ahead of you. The next moment, without warning, the tunnel begins to shrink and pinch off. If it closes completely while you're inside, the outcome would be catastrophic. You could be severed from both ends of spacetime, essentially stranded in a no-man's land of nothingness. Or more likely, you would be crushed and incinerated as the tunnel collapses like a squeezed straw. The implosion of space could release tremendous energy. Being caught in that would be unsurvivable. Matter and energy would be scrambled or ejected in unpredictable ways. It's a nightmare scenario, a gateway that vanishes while you're using it, leaving no trace of your passage. The idea of a wormhole collapse makes the prospect of stepping into one truly harrowing. It would be the ultimate trapdoor, one moment a pathway, the next a dead end, with the unfortunate traveller caught in between. In addition to the risk of collapse, there's also the possibility of extreme gravitational forces at the tunnel's throat. Tidal forces are differences in gravity from one end of an object to the other. They're what spaghettify objects falling into a black hole, stretching them into long strands. If a wormhole's throat is very narrow, or the curvature of space-time is very sharp, a ship or person passing through might be pulled apart by such gravity gradients. One end of your body could feel significantly stronger gravity than the other end, which would be fatal. You'd be torn in half, or worse, stretched into a thin ribbon of atoms. Essentially, traversing a poorly constructed wormhole could be as deadly as falling into a black hole. To avoid this, a traversable wormhole would likely need a wide mouth and gentle curvature, so that gravity's pull doesn't change too abruptly across a spacecraft or human body. That implies an even larger and more massive wormhole structure, which, in turn, demands even more exotic matter to stabilize. It's a vicious circle. Making the wormhole safer, by enlarging it and reducing tidal forces, also makes it even harder to create and maintain. It's a catch-22 written into the fabric of space-time. To make the wormhole safe, you must make it vast and energy-hungry, which pushes it even further out of reach. Even the space around a wormhole would have to stay quiet and undisturbed. A traversable wormhole might need to be kept far from any large masses or strong gravitational fields. If one mouth drifted too close to a planet or star, the external gravity could tug on the delicate structure and tear it apart. The fragile space-time tunnel could deform or collapse under the influence of a nearby gravity well. Science fiction often conveniently places wormhole portals near planets or space stations for easy access. Reality would likely be less accommodating. To stay stable, a wormhole might need to drift in relatively empty space, away from gravity sources that could disturb it. You might have to travel out to the middle of nowhere to even find the mouth of a stable wormhole. It would not be something you could safely anchor in Earth's orbit or on a planetary surface. In other words, even cosmic bystanders, stars, planets, or any massive bodies in the vicinity could spell doom for a fragile wormhole. In practice, this suggests that a functioning wormhole would need to reside in the quietest corner of interstellar space, a bubble of tranquility far from the gravitational storms of stars and planets. There's another layer of instability tied to the very fabric of cause and effect. Wormholes, by allowing faster-than-light paths, open the door to paradoxes, like sending a message into the past. Many physicists suspect that nature has built-in safeguards against such mischief. Stephen Hawking playfully dubbed this idea a chronology protection agency, implying that the universe enforces laws to prevent time travel paradoxes. In essence, the universe might not allow a wormhole to function as a time machine. It's a poetic notion, the universe acting as its own time police, ensuring that cause and effect can't be overturned by any shortcut through space or time. What might that safeguard look like? The theory suggests that if someone tried to manipulate a wormhole to send a signal back in time, physics itself would intervene and wreck the attempt. Calculations indicate that as soon as a wormhole could allow backwards time travel, a flood of energy would erupt within it. Quantum fluctuations, normally tiny, random energy blips that occur everywhere, would rapidly build up within the wormhole. They'd amplify into a raging storm of radiation and particles. Like feedback howling from a speaker, the energy in the throat would spike toward infinity, according to the equations, potentially blowing the wormhole apart at the very moment someone tried to create a time loop. It's as though the wormhole develops a self-destruct mechanism, an internal storm that ensures the portal cannot be used to violate time's order. The universe, in this speculative scenario, protects chronology by making a wormhole destroy itself if misused for time travel. Uncertainty remains about the exact outcome. Our understanding of quantum gravity isn't complete. But Hawking's conjecture is that the laws of physics ultimately prevent any time-traveling shenanigans. In Hawking's view, the universe might always find a way to preserve causality. If a wormhole arrangement would create a time paradox, physics might unleash intense effects, like that vacuum energy pileup, to stop it. It's a bit like an alarm system. Try to use the wormhole for time travel, and you trigger an explosion that slams it shut. While this idea is theoretical, it underscores how unforgiving wormhole physics could be. Even using a wormhole for something as seemingly innocent as sending a fast message can raise deep issues of cause and effect. The moment you try to exploit a wormhole in a way that breaks the usual rules, like sending information to your own past, the universe might pull the plug. It's a poetic notion, the universe acting as its own time police, ensuring no paradoxes can survive. Taken together, these issues paint a daunting picture. Even if we could conjure a wormhole, keeping it stable and safe seems nearly impossible. A traversable wormhole could be prone to catastrophic collapse at the slightest provocation. Hardly a reliable bridge for travel. The environment around it would have to be controlled and calm, far from any stray gravity or energetic events. Travelers would face not only the prospect of a tunnel snapping shut on them, but also potentially intense tidal forces or bursts of radiation if things go awry. In short, using a wormhole as a cosmic gateway might be far more perilous than the ordinary void of space it's meant to shortcut. Wormholes, in this light, are not friendly cosmic highways, but booby-trapped passages that resist being tamed. Given these challenges, some thinkers have asked, if wormholes can't safely ferry people or ships, could they at least send a signal? Perhaps the gentlest use of a wormhole would be not as a doorway for matter, but as a conduit for information. A flicker of light, a whisper of radio waves, just a message sent across the cosmos in an instant. Maybe a wormhole just big enough to transmit a communication could be made with a bit less energy, and maybe it could be kept stable since we wouldn't be shoving large masses through it. It's a tantalizing idea, using a tiny precarious wormhole not to travel ourselves, but to let our voices echo between the stars. In the quiet aftermath of all the dangers and difficulties, this more modest hope emerges. For a moment, consider not the grand dream of crossing the cosmos in person, but the simpler task of bridging the communication gap. If transporting people is too perilous or too costly in energy, perhaps a wormhole could at least carry our words. The concept is beguiling. Imagine two distant planets, light years apart, yet sharing a conversation in real time. No more waiting decades or centuries for radio signals to crawl between star systems. With a tiny wormhole acting as a cosmic wire, a whisper from one end of the galaxy could be heard at the other end instantly. The idea turns a wormhole into a sort of interstellar telephone line. We wouldn't go through it, but our messages would. Just the thought of it feels like science fiction come to life, a universe where distance is no barrier to conversation. Picture a practical scenario. An astronaut explorer lands on a planet 100 light-years from Earth. Under normal circumstances, if they radioed a message home, it would take a century for Earth to hear it, and another century for the astronaut to get a reply. Nearly 200 years for a full exchange. The astronaut could only hope that their distant descendants might hear back from Earth. But if a tiny wormhole link were established between that distant world and Earth, communication could be instantaneous. The astronaut could speak through the wormhole as if on a phone call, and mission control would answer without any delay. A question that once would take generations to resolve could now be answered in the same conversation. Loved ones could see and hear each other across impossible distances, sharing laughter and comfort in real time, despite being light years apart. Such a connection would erase the vast loneliness of space, making interstellar distance feel irrelevant when it comes to staying in touch. In such a future, isolation between worlds would be a thing of the past. In theory, a wormhole used only for signals could be minuscule, perhaps just big enough for a beam of light or a stream of particles to pass through. We wouldn't need a person-sized tunnel. A pinhole in spacetime might do. Maintaining a tiny wormhole might, one hopes, require less exotic matter than a gargantuan one meant for ships. It's the difference between drilling a narrow straw versus carving out a highway. The hope is that a microscopic or millimeter-scale wormhole could carry data, pulses of laser light, or perhaps quantum signals, and be slightly more achievable or stable. We might never master the titanic energies to send a starship, but sending a bit of information could be a nearer target, relatively speaking. Of course, slightly more achievable, in this context, still lies at the edge of imagination, a subtle shift from outright impossible to barely conceivable. Even so, it suggests a hierarchy of miracles. Maybe nature won't let us move mass through a wormhole, but perhaps a whisper of light might be allowed. The implications of wormhole communication are breathtaking. Distance would lose its sting. A research base orbiting a distant star could talk to Earth almost as easily as making a phone call. Messages across the galaxy would be effectively instantaneous, linking far-flung worlds into a network of shared knowledge and culture. Entire colonies light years away could remain in constant contact, coordinating with home or other colonies without the tyranny of light-speed delays. Some have even speculated that advanced alien civilizations, if they exist, might use such channels to converse, meaning they wouldn't need to broadcast signals we could detect. Perhaps the cosmos isn't truly silent. It could be full of conversations whispering through wormholes, entirely undetected by our normal means of listening. It's a fanciful idea, but it highlights how profoundly a wormhole link could transform our experience of the universe. It turns the unimaginable scale of space from a barrier into a bridge, profoundly altering how we might see our place in the cosmos. It transforms the galaxy from a vast, disconnected sea of stars into something like a tight-knit web of communities, at least for those connected by wormholes. It would change the narrative of isolation and vastness into one of connectivity and immediacy. One might wonder, if sending people through wormholes raises those perilous paradoxes, what about sending messages? In theory, any faster-than-light communication, which a wormhole link would be, can also lead to causality problems. Einstein's special relativity tells us that sending information FTL, faster than light, can, in certain frames of reference, look like sending information back in time. A clever arrangement of moving wormhole endpoints might let a message return to its origin before it was sent, creating a potential time loop paradox. The same chronology protection concerns we discussed earlier would apply here. Many physicists suspect that if wormhole communication is possible, the universe would still find ways to prevent paradoxical situations. Perhaps you couldn't move the wormhole ends freely without destabilizing them, or any attempt to configure a wormhole network for time travel would trigger those violent quantum effects. As long as one uses the wormhole to chat in the present, so to speak, these issues might be avoided. But the mere fact that we have to consider causality, even for conversations, shows how radical the wormhole idea is. It brushes up against the fundamental order of cause and effect. In contemplating wormhole communication, we brush up again against the universe's most fundamental guardrails. It's as if even the act of speaking through a wormhole needs the universe's permission to avoid cracking the timeline. Naturally, even this cosmic telephone idea is rife with challenges. It still demands at least a tiny traversable wormhole, which means conquering the exotic matter problem on a smaller scale. Achieving a stable mini-wormhole would likely require breakthroughs in physics and technology far beyond our current reach. In other words, even a mini-wormhole is an extraordinarily daunting prospect. At present, even a microscopic wormhole is an engineering dream beyond any horizon we can see. It's one thing to talk about it in theory, it's another to imagine building and maintaining one in practice. It's also important to realize that wormhole communication would be more like a private channel than a broadcast. A wormhole connects one specific location to another, like a tunnel, not a radio wave that spreads out in all directions. So to communicate with a distant colony, you'd need to have a wormhole endpoint already at that colony. In practical terms, that might mean creating a pair of linked wormhole mouths in one place, then physically transporting one of them to the remote destination by conventional means, a journey that could still take years or centuries. Only after that arduous setup could instantaneous communication commence between those 2 points. It's a mind-bending logistical challenge, essentially creating a pair of matched doorways in one place, then laboriously delivering one of them to a far-off world so that instant conversation can commence. In this sense, establishing a wormhole network would be akin to laying down cosmic infrastructure. Think of the first transoceanic telegraph cables. Enormous effort went into placing a physical line across the ocean. But once it was done, 2 continents could speak in seconds rather than weeks. Similarly, each wormhole link would require a colossal one-time investment to set up across the vast distances of space. You might spend 100 years sending a wormhole mouth to a target star, perhaps via a slower-than-light ship. But once it's there, that star system is connected back to Earth with zero delay. It's like building the ultimate communication bridge. If that could be achieved for multiple stars, those links might form a galactic web of communication. It's a staggering vision. Star systems connected by tunnels through space-time, whispering to each other across the void with no delay. It would herald a new era, a galactic web of minds and cultures connected not by the slow footsteps of light-speed signals, but by the instantaneous threads of wormhole links. The technical challenges are enormous, but the payoff would be the end of cosmic isolation. So far, wormholes remain purely theoretical. We have no evidence they really exist. Yet we spend a great deal of thought imagining how they might work, whether as perilous doorways for adventurers or as cosmic telephone lines connecting civilizations. That in itself says something about these tunnels through space-time. They capture our imagination like few other ideas in physics. Wormholes let us dream about breaking the ultimate limits of distance and time, offering a tantalizing escape from the ordinary rules of the cosmos. Perhaps that's why wormholes have become so popular in our stories and art. They are the ultimate cosmic shortcut, a mysterious portal that can instantly whisk you to far-off worlds. In countless science fiction films, novels, and video games, wormholes are depicted as swirling gateways or glowing tunnels through the stars. Through these vivid portrayals, the wormhole transformed from a dry theoretical concept into a visual icon that even children recognize. A swirling doorway in space, promising adventure. Even if actual physics may never allow such travel, the idea of a wormhole has left a profound mark on our collective imagination. Through these vivid portrayals, wormholes have become part of our cultural imagery of space exploration. It's remarkable that a concept which began as a quirk of Einstein's equations has become a familiar part of pop culture's cosmic vocabulary. Science fiction, in particular, has given us striking visuals of wormholes. In some stories, wormholes are depicted as shimmering gateways constructed by advanced technology. Think of the circular Stargate portal that instantly links distant planets. In the film Interstellar, a wormhole near Saturn was portrayed not as a flat door, but as a translucent sphere floating in space, through which astronauts could see a distorted image of another galaxy. It was a beautiful and scientifically inspired rendering, showing a wormhole as a spherical window warping the starlight. This portrayal, developed with the help of physicist Kip Thorne, gave audiences a scientifically grounded vision of what traveling through a wormhole might entail. It was a rare moment where Hollywood spectacle met scientific authenticity, giving viewers the eerie feeling that if wormholes exist, they might indeed look something like that. Other movies and shows have imagined wormholes as crackling energy storms or luminous tunnels that twist and turn. Dramatic, visual shorthand for tearing through the fabric of space. Each creative portrayal adds to our mental gallery of what a wormhole might look and feel like. They let us visualize the impossible in a way that feels almost real. We can picture a spaceship approaching a swirling portal, the leap into the unknown, the wild ride through psychedelic lights. It's a testament to human creativity. We have painted these impossible journeys in such vivid colors long before we have any proof they could be real. Wormholes have featured in countless creative works over the decades. In the novel Contact by Carl Sagan and its film adaptation, scientists discover a transportation network of wormholes created by an advanced civilization, allowing near-instant travel across vast distances. This idea was directly informed by real physics. Sagan consulted Kip Thorne to make the wormhole travel in contact as plausible as possible. In the Star Trek Deep Space Nine series, a stable wormhole is a central element, serving as a gateway to a distant quadrant of the galaxy and fundamentally shaping the politics and story of that show's universe. From novels to television, the wormhole has become a go-to plot device whenever storytellers need to bridge cosmic distances quickly. Audiences immediately grasp the concept. Step in here, pop out light years away over there. Even if we know it's speculative, we embrace it as a tantalizing possibility. It symbolizes the hope that perhaps one day we too could overcome the immense gulf between the stars in a single leap. In fiction, wormholes satisfy our deepest wanderlust. They allow our stories to leap beyond the confines of physics, carrying us to the farthest reaches of imagination. Even physicists rely on visual analogies to grapple with wormholes. Textbooks often illustrate a wormhole by drawing space as a two-dimensional sheet, folded so that two distant points touch, then connecting them with a short pipe, the wormhole. Another common image shows two funnel shapes, often drawn like curved surfaces on a graph, joined at their narrow ends, representing two regions of space connected through a tunnel. These simplifications help our minds grasp what the complex mathematics is saying. In fact, the very term wormhole itself is an analogy from nature, a worm tunneling through an apple to get to the other side, instead of crawling around the surface. Such images and comparisons turn an abstract concept into something we can picture, making the idea of these space-time tunnels a bit more accessible to human intuition. Through these vivid mental pictures, we bring the wormhole out of pure theory into a realm we can play with in our imagination. They are imaginative crutches that allow us to discuss seriously something we've never seen. It's notable that wormholes were born not in a sci-fi story, but in scientific discourse. The concept goes back to 1935, when Albert Einstein and his collaborator Nathan Rosen discovered, in theory, what they called a bridge in spacetime. Essentially a connection between two separate points, now known as an Einstein-Rosen bridge. This was the first glimpse of what we now call a wormhole, and it appeared as a mathematical oddity in Einstein's general relativity equations. At the time, it was just a curiosity. Nobody thought you could actually travel through such a bridge, especially since it pinched off too quickly, as later analysis showed. Decades later, in 1988, Kip Thorne and colleagues published a famous paper analyzing what it would take for a wormhole to be traversable by humans. Interestingly, Thorne was prompted by the needs of a science fiction story, Carl Sagan's Contact, to figure out if physics could allow a character to travel through a wormhole without dying. Thorne's calculations introduced the requirement for exotic matter and explored time travel paradoxes, essentially bringing wormholes into the realm of serious scientific inquiry. This interplay of fiction and science is fascinating. A novelist's question led to one of the seminal scientific papers on wormholes. Since then, wormholes have been a legitimate, if highly speculative, topic in theoretical physics. Papers have been written exploring their stability, how they might appear to observers, whether quantum mechanics could permit them, and how they relate to things like black holes and entanglement. It's a great example of how human imagination, through both fiction and science, works together to expand our understanding. The fiction inspired rigorous analysis, and the physics in turn inspired even more imaginative stories. Thanks to this interplay, wormholes have a firm foothold, both in our scientific literature and our science fiction lore. There is something deeply appealing about the wormhole idea that goes beyond the technicalities. It speaks to our age-old yearning to leap beyond boundaries. Throughout history, whenever we encountered a vast distance or a daunting journey, we imagined shortcuts, from sailors dreaming of a northwest passage, to connect oceans, to to engineers carving canals through isthmuses to save ships from long detours. A wormhole is the ultimate shortcut, the cosmic Northwest Passage, a hope that maybe the universe has hidden back doors that make the impossible journey possible. In our mind's eye, it represents the idea that we might one day outwit the vastness of space and time. It's a symbol of exploration and ingenuity, a reminder that even faced with the immense scale of the cosmos, we don't simply sigh and give up. We dream of clever ways to transcend our limits. Wormholes, as a concept, encapsulate that audacity. They say, what if distances of light years could be crossed in a heartbeat? They allow us, at least in our dreams, to be galactic travelers without the shackles of light speed. It's the same spirit that drove humans to cross oceans and launch rockets, projected onto an even grander canvas. And even if wormholes remain forever hypothetical, just thinking about them has enriched both science and storytelling. They push us to ponder the extremes of physics, warped space-time, causality paradoxes, negative energy, ideas that test the edges of what we know. In grappling with wormholes, scientists have had to confront the need for a theory that merges quantum physics with gravity, since wormholes bring up issues, like the vacuum energy explosion in time travel scenarios, that demand a quantum gravity understanding. In that sense, wormholes serve as thought experiments that probe the limits of our theories and sometimes illuminate where those theories break down. They stimulate new ways of thinking about space, time, and information. On the philosophical side, they force us to question things we take for granted, like the unbreakable flow of time or the fixed separation of distant places. Above all, the wormhole is a vessel for our hopes and curiosity. It symbolizes the idea that the universe might have secret paths waiting to be discovered, and that perhaps we won't always be prisoners of distance. It's the embodiment of the classic science fiction dream that advanced knowledge could make the impassable passable. The enduring fascination with wormholes ensures that we will keep them in mind as we explore theoretical physics and cosmology. Who knows? Someday, new physics, maybe from a theory of quantum gravity or extra dimensions, could reveal mechanisms that make wormholes less fantastical than they seem now. Until then, wormholes remain a guiding light in our imagination, urging us to wonder and to question. For the time being, they are tantalizing what-ifs, inspiring us to dream big while we continue the slow, steady work of advancing science. After all, the cosmos still holds vast unknowns, and the human spirit will forever seek ways to bridge the gaps, even if it means conjuring up tunnels through space and time in the mind's eye. As our journey through these ideas continues, we carry forward that sense of wonder. We haven't reached the end of the story, far from it. The next cosmic horizon awaits, and with it, perhaps new insights or discoveries that today we can barely imagine. Wormholes remind us that even the wildest ideas can spark real progress, and that the universe may yet surprise us with pathways currently seen only in our dreams. Imagine a tunnel through space-time, a wormhole, connecting two distant points in the universe. Albert Einstein and his colleague Nathan Rosen first theorized such a bridge in 1935, envisioning a shortcut through the fabric of reality. But later studies revealed a serious problem. This hypothetical wormhole would collapse almost as soon as it formed, pinching off too quickly for even a ray of light to pass through. In essence, the cosmic shortcut snaps shut immediately, as if the universe refuses to hold such a door open. For decades, wormholes remained an intriguing yet impractical idea, a tantalizing solution that nature seemed to forbid as quickly as it appeared. Physicists in the late 20th century began searching for ways to keep a wormhole open. In the 1980s, Kip Thorne and his colleagues proposed a clever workaround for the collapsing tunnel. Thread the wormhole with an unusual form of matter that has negative energy, often called exotic matter. Unlike normal matter, which pulls inward with gravity, this hypothetical negative energy matter would push outward, exerting a sort of anti-gravity effect. By lining the wormhole's throat with this exotic material, they showed in theory that the tunnel's walls could be held apart, preventing it from pinching closed. In other words, the wormhole could be propped open, allowing something, or someone, to travel through without being crushed. This concept transformed wormholes from a fleeting curiosity into something potentially traversable, on paper, at least. Crucially, negative energy isn't pure fantasy. Quantum physics allows it in small doses. For example, the Casimir effect in the lab can produce a region of space with slightly less energy than the normal vacuum, effectively a negative energy density. Theoretically, quantum fields even permit states where energy at a point can be arbitrarily negative for brief moments. Renowned scientists like Stephen Hawking and Kip Thorne argued that such quantum effects might be harnessed to stabilize a wormhole's throat. The catch is that generating and gathering enough exotic matter to hold a human-sized wormhole open is far beyond our current technology. It would require quantities or arrangements of negative energy that we don't know how to produce. Still, the fact that physics doesn't outright ban negative energy, and even provides examples of it on tiny scales, gives a glimmer of hope that traversable wormholes might not be fundamentally impossible, just extremely difficult to engineer. Interestingly, some scientists have speculated that wormholes might have naturally formed under extreme conditions in the early universe. If a tiny wormhole popped into existence during the Big Bang, and was somehow threaded with a peculiar cosmic structure, having negative mass, the rapid inflation of the young universe could have blown that minuscule tunnel up to macroscopic size. In theory, such a relic wormhole could still be drifting in space today, hidden among the stars. Likewise, it's been proposed that countless microscopic wormholes might permeate the quantum foam of spacetime, flickering in and out of existence beyond our ability to see, perhaps even contributing to the unseen mass we call dark matter. These ideas are highly speculative, but they raise a tantalizing possibility. Wormholes need not be purely the stuff of imagination. They could be real phenomena, scattered through the cosmos, or lurking in exotic realms of physics, waiting to be discovered. And if a wormhole could truly be stabilized and kept open, it might do more than bridge space. It could also bridge time, introducing the extraordinary question of whether a wormhole could double as a time machine. Space and time are not separate in Einstein's universe. They form one interwoven fabric. A wormhole, therefore, links not just two locations in space, but 2 points in time as well. If one mouth of a wormhole is accelerated to near light speed, or kept in a stronger gravitational field, while the other stays put, time will flow differently for the two ends, a result of relativistic time dilation. Suppose you did this, and then brought the two ends back near each other. The travelling end would have aged less. It becomes younger than the stationary end. Now imagine stepping into the younger mouth and emerging from the older mouth. You would come out before you went in, effectively travelling backward in time. In essence, the wormhole becomes a pathway through time as well as space, a sort of time machine. This scenario comes with an important limitation. A wormhole time machine cannot send you back to a time earlier than the moment the wormhole first became operational as a time device. In other words, you couldn't travel to before the wormhole existed or was stabilized. If a wormhole were created or modified for time travel in the year 2100, that would be the earliest point in history one could reach using it. You might go from 2200 back to 2100 through the wormhole, but not to 2099. The technology provides a tunnel into the past, but its entrance is anchored to that creation moment. This built-in constraint prevents using wormholes to visit epochs before their own existence, meaning no trips to the dinosaur era unless a wormhole was around back then. It's a modest consolation that preserves some order. The wormhole time machine is more like a bridge through time with a definite starting point, rather than a free-ranging time ship that can go anywhere, anywhen. The notion of a wormhole time machine leapt from speculation to serious scientific discussion in 1988. That year, Kip Thorne and his collaborators published a landmark paper outlining how a traversable wormhole could be converted into a time portal without violating known physical laws. It was a revolutionary realization. General relativity did not explicitly forbid a loop in time, provided you had a traversable wormhole and the requisite exotic matter. The media seized on the idea. Newspapers and magazines dubbed Thorne the man who invented time travel, a sensational label he was not entirely comfortable with. For a moment, the stuff of science fiction had stepped onto the pages of scientific journals and the evening news. The physics community, both excited and wary, began scrutinizing the proposal from every angle, looking for any hidden inconsistencies or cosmic paradoxes that might arise. After the initial wave of enthusiasm, researchers knew that if nature allowed a time-traversing wormhole, it would raise as many questions as it answered. As scientists examined these wormhole time machine ideas more closely, they found reasons to be cautious. Thorne himself, after the early burst of enthusiasm, grew more skeptical by the early 1990s, when further calculations suggested that any attempt to use a wormhole for time travel might trigger its own ruin. It appeared that quantum effects could pile up when you try to make a time loop, potentially flooding the wormhole with radiation and causing it to destabilize or self-destruct. Stephen Hawking offered a famously wry response to the whole concept. He proposed a chronology protection conjecture, essentially a built-in law of physics that prevents closed time loops and thereby keeps the world safe for historians. In Hawking's view, something, perhaps a surge of energy or other quantum calamity, would always intervene to prevent a wormhole from functioning as a time machine. After all, he pointed out, if future humans eventually invent time travel, why haven't we been inundated with time tourists popping up at historical events? It's a sharp question with no answer in sight. The implication is that perhaps the universe simply does not permit these causality-violating trips. Thus, even as wormholes invited us to dream of time hopping, many physicists suspected that nature had subtler rules to forbid it. And those suspicions led directly to the next issue, the paradoxes lurking in the shadows of time travel, and how the universe might deal with them. For anyone dreaming of using a wormhole as a time machine, the spectre of paradox is unavoidable. The classic example is the grandfather paradox. Imagine traveling back in time and accidentally preventing your grandparents from meeting. If that happened, you would never be born. But then who traveled back to interfere in the first place? Such a logical contradiction makes it seem that something must prevent it from happening. Cause and effect, once tangled in a loop, threaten to break down our sense of reality. Wormholes that enable backward time travel would bring these science fiction conundrums into the real world of physics, demanding some resolution. How could the universe make sense of situations where an effect can erase its own cause? Physicists have proposed a few intriguing escape routes to avoid these paradoxes, assuming wormhole time travel were possible. One idea, championed by Russian physicist Igor Novikov, is that the universe might enforce self-consistency. In other words, any event that would create a paradox is simply forbidden from occurring. This is the Novikov self-consistency principle. If you go back in time, you might influence events, but only in a way that is compatible with the history that already unfolded. You could become part of the past, but you couldn't change the outcome in a contradictory manner. In this view, the timeline adjusts around your actions to ensure there's no inconsistency. The probability of you creating a true paradox is zero, because the universe won't allow those paradox-causing initial conditions. You might try to prevent your grandparents from meeting, for instance, but something would inevitably thwart the attempt, or your actions would inadvertently end up ensuring they do meet, preserving the consistency of history. A famous thought experiment illustrates how self-consistency might work. Physicist Joseph Polchinski posed a scenario. Imagine a billiard ball that travels through a wormhole and emerges in the past, on course to collide with its younger version. At first glance, it seems the older ball could knock the younger one off course, preventing it from entering the wormhole, a paradox. But when Thorne and his students analyzed this setup, they found a self-consistent solution. The billiard ball coming out of the future hits its younger self at just the right angle to deflect, not stop, its trajectory. The younger ball still goes into the wormhole, just in a slightly different direction, which in turn causes it to emerge and deliver the same glancing blow to its younger self. In this scenario, every action the ball takes in the past contributes to a consistent loop of events. There's no contradiction. The ball's interference turns out to be exactly what ensures it enters the wormhole in the first place. This clever resolution shows how the universe could, in principle, allow time loops as long as they are logically self-consistent. The timelines sort themselves out so that cause and effect form a closed, unbroken cycle with no loose ends. Another possible escape from paradox is the idea of parallel timelines, or multiple universes. In this interpretation, if you travel back and alter something, you may actually be jumping onto a different timeline, leaving your original history intact. So you could say, go back and prevent your grandparents from meeting. But that act would create or belong to a new alternate universe in which you were never born, while your original universe, where you did exist and embarked on the time trip, remains unchanged. This is akin to the many worlds interpretation of quantum mechanics applied to time travel. Every time a paradox-threatening event would occur, the universe splits and diverges into consistent branches. Some researchers have suggested that wormhole-enabled time travel might operate this way by default, that a wormhole connecting different times actually connects different parallel universes or splits the timeline, thus avoiding true paradoxes. In one universe, your grandfather lives. In the new branch, he doesn't. And the two timelines never mix to cause a logical inconsistency. It's a mind-bending solution, essentially saying that you can change the past, but not your past, only the past of a newly created reality. This would eliminate paradoxes at the cost of spawning alternate realities with each major alteration. Then there is Hawking's more no-nonsense approach. Nature simply vetoes time paradoxes by preventing them from ever happening. His chronology protection conjecture is an embodiment of this idea. The universe might have mechanisms that make wormhole time travel self-defeating. We touched on this earlier. Perhaps if you try to use a wormhole to go back in time, physics will respond with a surge of disruptive energy that seals the wormhole or causes it to collapse at the critical moment. It's as if the universe has a built-in safety switch that flips off the moment a timeline loop threatens causality. In the case of the wormhole, calculations, by Matt Visser and others, have indicated that bringing the two ends of a wormhole together to form a time loop could induce intense quantum effects, like radiation feedback, that either push the wormhole mouths apart or destroy the tunnel, thereby averting the time loop paradox. Under chronology protection, no matter how advanced your technology, the wormhole would refuse to cooperate in creating a violation of cause and effect. This would make the timeline safe at the very cost of forbidding time travel. It's a conjecture, not proven, but it aligns with the observed absence of any paradoxical mess in the universe around us. As far as we can tell, causality has never been violated, which might be because the laws of physics make sure of that, by one means or another. Which of these resolutions, self-consistency, timeline branching, or chronology protection, does our universe actually use? We don't know. Without a real wormhole time machine, or any kind of time machine, to experiment with, these ideas remain speculative. It could be that the universe quietly adheres to Novikov's principle, and no paradoxical event ever comes to pass. Or maybe if we tried, we'd slip into a parallel universe and never realize it. It's also quite possible that Hawking is right, and the universe won't even give us the chance. Any attempt to tamper with causality would be snuffed out by physical law. Until we have empirical evidence, the paradox question remains a maze of what-ifs. Still, exploring these possibilities has been illuminating. It forces physicists to clarify the laws of nature at extreme conditions, and to consider whether consistency and causality are deeply protected principles. In wrestling with these phantom time travelers and their logical knots, we learn more about what our universe might allow or forbid. All this theoretical soul-searching eventually points back to reality. Do wormholes actually exist out there? And if they do, how would we find one? So far, our journey has been through mathematics and thought experiments, but nature might have its own answers hidden in the cosmos. The next step is to look outward, to search the stars and galaxies for any sign that wormholes are more than just theoretical musings. If the universe has already built some of these fantastical tunnels, even on the grandest scales, we should strive to detect their presence. The challenge is formidable. Wormholes, if they are out there, might masquerade as other phenomena or be very subtle in their effects. But scientists have begun devising strategies to hunt for the telltale footprints that a cosmic wormhole might leave behind. One obvious approach is to consider how a wormhole's gravity would affect light and matter around it. From a distance, a wormhole's gravitational pull would be much like that of a black hole of similar mass. Both would bend the path of light and influence the orbits of nearby objects. This means we might look for wormholes by looking for anomalies in gravitational lensing or in stellar motions. Gravitational lensing occurs when a massive object warps the light from a more distant object behind it, often producing multiple images or distorted rings of light. A wormhole could act as a gravitational lens. However, physicists have predicted that certain lensing signatures might distinguish a wormhole from an ordinary black hole. For example, calculations suggest a wormhole might magnify the light of a background star or galaxy far more strongly than a black hole would, potentially by a factor of 100,000 in some configurations. An enormous magnification that outstrips what we see from black holes. Additionally, the pattern of images could differ. Whereas a lone black hole might create two primary images or a fuzzy ring of lensed light, a wormhole might produce a more complex pattern, such as three distinct images of the background object, one significantly brighter than the others. Detecting something like that, an unusually high magnification lens with an odd number of multiple images, would be a strong clue that we've found not a black hole, but perhaps a wormhole. Astronomers are sifting through data from large sky surveys, looking for these kinds of outliers. It's a bit like searching for a needle in a haystack. Countless galaxies and black holes produce lensing effects, but maybe one or two will have that peculiar signature hinting at a wormhole. So far, none has been confirmed. Every gravitational lens observed to date can be explained with conventional massive objects. That said, our surveys and analyses are still improving. With each new telescope and instrument, optical, radio, gravitational, we cast a wider and more sensitive net. A wormhole, if one exists within our observational reach, would be a spectacular catch. Just the knowledge that such a thing is real would revolutionize physics. Because of that potential payoff, the search is very much alive, even if it has turned up nothing but intriguing false alarms thus far. Another avenue is to examine known astrophysical objects more closely. Take, for instance, the supermassive black hole at the center of our Milky Way galaxy, known as Sagittarius A. Some have wondered, could this actually be a wormhole in disguise? If a traversable wormhole were hiding at the galactic center, what would we expect to see? One idea is that if there were a connected passage, the gravity of mass on the far side of the wormhole might leak through and subtly perturb the orbits of stars on our side. Researchers have proposed looking at the precise motions of stars that swing very close to Sagittarius A to see if their orbits show any slight deviations that a hidden wormhole might cause. Over the past decades, astronomers have tracked stars, like the famous star S2, looping around the galactic center, and so far, their behavior matches perfectly with a standard black hole's gravity. No unexplained extra tugs or wiggles have been observed, which means if there is a wormhole there, it's not having an obvious effect on nearby stars. This places limits on certain wormhole models. For example, a large, stable wormhole with a lot of traffic would likely disrupt those orbits, which we don't see. While it doesn't entirely rule out a wormhole, it suggests that our own galaxy's center isn't blatantly broadcasting any wormhole-like clues. Perhaps the most futuristic search method involves gravitational waves, ripples in space-time that can be detected by instruments like LIGO. These waves are typically generated by massive objects like black holes or neutron stars spiraling into each other and merging. If wormholes exist, especially if one end of a wormhole can capture a black hole, they could produce gravitational wave patterns quite unlike the chirps we've recorded from binary mergers. Imagine a black hole orbiting a wormhole and eventually plunging into it. If the black hole goes through to some other universe or distant part of the cosmos, from our perspective, the gravitational waves might abruptly cut off, as if the object vanished mid-merger. Then, perhaps, if the black hole comes back through the wormhole, like bouncing back, the signal might reappear. The result would be a series of wave bursts with mysterious gaps of silence in between. In essence, the gravitational wave signal would blink on and off, or produce an echo after the initial merger signal, which is not something two ordinary black holes would ever do. Physicists have predicted that such an odd pattern, a chirp, then sudden quiet, then another chirp, would be a smoking gun indicator of a wormhole interaction. So far, we haven't seen any gravitational wave events that look like that. All detected signals have matched well with collisions and mergers of known types of objects. But the data is still young. We've been listening only since 2015, and our detectors are getting more sensitive. The universe might yet have some strange wriggles in space-time to show us. A single peculiar signal could reveal that a wormhole was involved in some cosmic dance. Researchers are actively searching the gravitational wave catalogues for any unexplained echoes or cuts. Essentially, anything that can't be explained by the standard playbook of black hole or neutron star mergers. It's a long shot, but the payoff would be enormous. Direct evidence that wormholes not only exist, but can interact with massive objects. Despite all these clever searches, the universe has remained conspicuously silent about wormholes. We have not found any phenomenon that we can definitively point to and say, that must be a wormhole. Every candidate clue has so far turned out to have a more mundane explanation or insufficient evidence. Wormholes, if they are out there, are hiding very well. It's possible that they simply are extremely rare, or they might exist in forms or locations that make them hard to detect. For example, microscopic wormholes flashing in and out of existence, or macroscopic wormholes located in the distant universe where we cannot observe them. It's also quite possible that nature truly doesn't produce traversable wormholes at all, and that they really are only artifacts of equations, or require conditions that don't occur naturally. The continuing null results are sobering, but each no we hear from the cosmos refines our understanding and encourages us to keep improving our methods. The search is far from over. After all, decades passed between the prediction of gravitational waves and their eventual discovery. The first gravitational wave wasn't detected until 100 years after Einstein predicted it. Black holes were theory for decades before astronomical evidence piled up. Wormholes may demand similar patience. Until we either find one or gather enough data to strongly rule them out, scientists will keep listening to the quiet and looking for any subtle hints written in the light of distant stars or the whispers of spacetime. At the moment, the wormhole is an enigma wrapped in silence. The universe keeps this secret, if it exists, well hidden. Unlike black holes, which have announced themselves through X-ray flares, gravitational waves, and even direct imaging, wormholes have given us no sign of their presence. This disparity is striking. Black holes, once purely theoretical, gradually became an observational reality. Wormholes, by contrast, remain purely hypothetical in 2025. The silence could be telling us something profound. Perhaps it tells us that wormholes are exceedingly scarce, or that they can only exist under conditions we have yet to encounter. It might even be telling us that traversable wormholes are forbidden outright by some fundamental principle we haven't fully understood. For now, we peer into the darkness and see no tunnels threading through space and time, only the void, punctuated by the well-behaved phenomena we recognize. Why might the universe be so quiet about wormholes? One possibility is that wormholes simply do not exist in a tangible, naturally occurring form. It could be that while the equations of general relativity permit these solutions, the real universe has no mechanism to produce them in a stable state. Perhaps the exotic matter requirement is too strict. Maybe no process in the universe churns out the right kind of negative energy in large amounts. If traversable wormholes require a kind of negative mass energy that doesn't actually occur outside of thought experiments, then of course we won't find any. It would mean our cosmos has black holes aplenty, which it does, but no wormholes larger than the quantum scale. In that case, wormholes might be relegated to mathematical curiosities or speculative engineering projects by advanced civilizations, if they too could overcome the exotic matter hurdle. The quiet might simply be the universe saying, "No, these bridges are not part of my natural architecture." Another possibility is that wormholes do exist, but they are exceedingly well hidden or subtle. They might be rare, or exist in forms that are hard to distinguish from ordinary objects. It's conceivable, for example, that some black holes might actually be wormholes, but so stable and quiescent that they behave exactly like black holes on the outside. If nothing ever travels through to reveal the other side, how would we tell? Wormholes might also be very small. Perhaps naturally occurring ones never grew larger than subatomic scales. In that case, trillions of tiny wormholes could be fizzing in the vacuum around us, and we'd have no direct clue. They would be too small to affect light or matter in noticeable ways. The universe could be teeming with wormholes at the Planck scale, the tiniest scale of length, popping in and out of existence as a kind of space-time foam. And we wouldn't perceive them. The silence in our telescopes might not mean wormholes aren't there. It might mean they whisper at frequencies we can't yet detect, in phenomena too subtle for us to notice. It wouldn't be the first time nature hid its strangest workings in the subtlest corners. Quantum mechanics taught us that. Wormholes could be part of the universe's repertoire, but hidden in the quantum realm or in distant galaxies beyond our observational reach. Interestingly, modern theoretical physics has opened a new perspective on how wormholes might be quietly woven into the fabric of reality. A conjecture known as ER equals EPR, proposed by physicists Juan Maldacena and Leonard Susskind, suggests that there could be a relationship between wormholes and quantum entanglement. In short, the idea is that any two particles that are quantum entangled might be connected by a very tiny wormhole, Einstein-Rosen bridge. ER standing for Einstein-Rosen, wormhole, and EPR for Einstein-Podolsky-Rosen, entanglement. If this bold idea is true in some form, it means wormholes might be ubiquitous in the quantum world, acting as nature's way of linking particles across distances. These wormholes would be on the quantum scale and not traversable in any ordinary sense. You couldn't crawl through one, any more than you could crawl through an entangled electron. But it's a profound suggestion that space-time connectivity and quantum connectivity are two sides of the same coin. In this picture, the universe does make wormholes all the time, but only as tiny, ephemeral threads that reflect quantum correlations. They would be everywhere and nowhere, utterly invisible to us except through the mysterious phenomena of entanglement. If the ER equals EPR idea, or something akin to it, is correct, then wormholes might indeed be one of the universe's best-kept secrets, present in principle in every quantum link, yet impossible to utilize for grand adventures, or even to detect in a direct way. The cosmos would be full of mini wormholes that reconcile quantum mechanics and gravity in the deep mathematical structure. But to us, they manifest only as subtle quantum effects, not as star-spanning tunnels. In the end, we're left with a cosmic silence and our own persistent questions. Wormholes remain theoretical possibilities, compelling, mathematically allowed, but empirically elusive. The universe's silence on them could be a nudge for us to develop new ways of listening. Maybe we need to invent radically sensitive instruments or observe for much longer durations. Perhaps a wormhole signature will show up unexpectedly in some data we collect in the future, a strange lensing event, or an odd gravitational wave, and we will only recognize it after the fact. Or maybe we'll have to create one ourselves, in some far future, when our technology catches up with our imagination, to truly know if they can exist. For now, the story of wormholes is one of maybe and what if, supported by the pillars of theory, but awaiting the touch of evidence. The universe keeps many secrets, and this appears to be one of them. Yet, as history has shown, today's secrets can become tomorrow's revelations. So we continue to watch the skies and refine our theories, hopeful that one day the silence will break. And as we prepare to venture further into this mystery, we carry with us the wonder that wormholes inspire, the dream of tunnels through space and time, forward into the next chapter of our exploration. Long before the word wormhole existed, people have dreamed of hidden doorways to other worlds. Since ancient times, our myths and legends have been filled with passages to realms beyond ordinary life. In the earliest stories recorded on clay tablets, heroes journey through secret portals seeking gods or paradise. It seems that even in humanity's infancy, we imagined that somewhere, if one only found the right door, an entirely different world could be reached. The idea of stepping through an opening and vanishing into a different realm is as old as storytelling itself. For every generation, tales of hidden doorways have sparked wonder and speculation, hinting that the world might hold more than meets the eye. In mythologies across the world, these portals took many forms. The ancient Greeks believed the entrance to the underworld lay hidden in certain caves at the edges of the known world. In one famous tale, the poet Orpheus steps into the darkness of a cave at Cape Tainaron, believing it to be the doorway to Hades itself. He descends into the underworld in search of his lost love, crossing the threshold between life and death through that secret passage. Far to the east, in Mesopotamian legend, King Gilgamesh is said to travel through a tunnel inside a distant mountain, hoping it will lead him to a paradise where the gods might grant him eternal life. Across cultures, people envisioned that sacred caves, mountain passes, or holy rivers might hide gateways to realms beyond human reach. In each case, crossing that threshold was a momentous act, often marked by courage, desperation, or a touch of divine guidance. Imagine an ancient poet in Greece, standing at the mouth of a lonely cave by the sea. The legend says this cave is an entrance to the underworld. He takes a deep breath and steps into the darkness. The daylight fades behind him as he follows a winding path, lit only by the faint glow of fungi on damp walls. With each step, the air grows cooler and the silence deeper. He doesn't know if he will ever return, but love drives him onward. In that moment, the cave is no mere cave. It is a portal, a doorway between the land of the living and the realm of the dead, and he has dared to cross it. In Norse legend, a glowing rainbow known as the Bifrost was imagined as a bridge linking Earth to Asgard, the realm of the gods. Many faiths and folklore traditions spoke of a route between our world and another. Sometimes it was pictured as a ladder into the sky, or a path revealed only to the worthy. It could be a shimmering arc of light, or a hidden door in an ancient tree. Whatever the form, the message was the same. Somewhere, a link existed between the everyday world and a realm beyond our reach. Or picture a time in ancient Ireland, on the eve of Samhain, what we now call Halloween. A warrior walks alone at midnight across misty fields. He approaches a ring of standing stones on a hilltop that local legend deems a doorway to the fairy realm. The air is cold and strangely still. As he steps into the circle, the wind picks up and the stones seem to shimmer. The veil between worlds is thin on this night. He feels a tingling in the air. In the next heartbeat, the scenery around him changes. He finds himself in a twilight land of eternal summer, the realm of the Shidi, where music and laughter echo from distant hills. For this warrior, the stone circle has become a portal, transporting him to a place of legend that few mortals ever see. As the centuries passed, the fascination with hidden doorways only grew. In more recent folklore and literature, these portals moved into fairy tales and fantasy. Children's stories brimmed with secret passages to magical lands just out of sight. Alice followed a white rabbit down a hole and tumbled into Wonderland. A curious girl stepped through a looking glass into a world turned upside down. In another tale, 4 siblings pushed past old coats in a wardrobe and found themselves in the snow of a mystical kingdom. Even a Kansas farm girl was swept by a whirlwind and awakened in the colourful land of Oz. Different as these stories are, each offered the same wonder. An ordinary person discovers a gateway to a realm of marvels. For example, the portals in these tales often appear in mundane places: a rabbit hole in a garden, an old wardrobe in an attic, a sudden cyclone on a farm. Such unassuming gateways gave a sense that magic could be hiding anywhere, just out of sight. Portals soon became a staple of modern storytelling. Think of the many iconic scenes etched in our collective memory. A train platform that magically leads to a school for wizards. A glowing doorway activated by ancient symbols that sends explorers to distant planets. A mirror that doubles as a gateway to a parallel universe. These moments resonate because they tap into that age-old idea in a new guise. As technology advanced in the real world, our fiction kept pace by giving portals a scientific twist. What used to be accomplished by magic wardrobes and rabbit holes began to be achieved by futuristic devices and cosmic phenomena on the page and screen. By the 20th century, the portal idea leapt from myth and magic into the realm of science fiction. The laws of physics themselves hinted that shortcuts through space and time might be possible. Scientists like Albert Einstein and Nathan Rosen theorized about bridges in the fabric of spacetime, later dubbed wormholes, that could connect two distant points. Before long, storytellers seized on this notion. In movies and novels, adventurers began to step not through fairy rings or enchanted mirrors, but through technological gateways built with alien science or future human innovation. A shining ring of energy might stand in a secret lab, waiting to transport explorers to far-off worlds. A starship might encounter a mysterious cosmic tunnel that slings it to the other side of the galaxy in seconds. The ancient dream of instantaneous travel found a new life, wrapped in the language of space-age science. Audiences thrilled to the thought that physics itself might permit the fantastical journeys once limited to fairy tales. Across all these myths and stories, the details may change, but the fascination endures. There is something universal in the idea of a portal to elsewhere. It speaks to a deep yearning within us, a hope that there is more than the world in front of our eyes. These tales of secret doorways invite us to wonder what we would do if we found one. Why, across thousands of years, have humans been so enchanted by the notion of a hidden gateway? Perhaps it is because deep down, we have always been wanderers at heart. Human beings have an innate restlessness, a curiosity that drives us to imagine what lies beyond the next hill or behind a closed door. Since our earliest days, we have pushed against the boundaries of our world, first walking over distant horizons, later sailing across unknown seas. And when every land was mapped, we looked upward to the stars. The yearning for some elsewhere seems to be a fundamental part of who we are. On a quiet night, under a sky full of stars, it's easy to feel that pull. You might stand at your window and gaze upward, wondering what it would be like to slip the bonds of Earth and step out there among the glittering lights. That urge to go further, to find something beyond the here and now, stirs in the human heart across continents and centuries. Our ancestors felt it when they reached the ocean's shore and yearned to know what lay beyond the waves. We feel it now when we contemplate worlds orbiting distant suns and wish we could visit them in a heartbeat. That endless curiosity might explain our fascination with portals. Where ordinary travel fails, the imagination steps in to bridge the gap. When we hit the limits of what ships and roads can conquer, we invent secret passages to keep exploring. If a far-off paradise or a new world is out of reach, the mind finds a way, a hidden door, a sudden magic corridor, to take us there at least in fantasy. Portals are the perfect symbol of our refusal to accept boundaries, a promise that there is always a way to go further. For many people, the idea of a doorway to another world is also about escape and hope. Reality can at times feel confining or disappointing. And who hasn't daydreamed of finding a way out, a path to a place where problems melt away? In stories, portals often lead to realms of wonder or peace, offering a chance to leave troubles behind. Children hiding from wartime bombings could imagine climbing through a magical wardrobe to safety and adventure. Adults with ordinary routines might secretly yearn to stumble on a portal that whisks them to a life of excitement. In our collective imagination, that hidden gateway promises a release from the limits and sorrows of the here and now. That longing has even motivated real-world quests. Throughout history, adventurers and explorers have searched for places rumoured to be earthly paradises or gateways to something greater. Think of the tales of a fountain of youth, a spring that could grant eternal life to those who found it, or the legend of El Dorado, a hidden city of gold promising unimaginable riches. While these quests often ended in disappointment, the impulse behind them was much like the desire for a magical door, a belief that somewhere, if one could only find it, a miraculous escape or reward awaited. These legends show that our portal fantasies are not confined to storybooks. They echo in the journeys and aspirations of real people across time. In a sense, our obsession with hidden doorways might be a metaphor for something even deeper. It reflects an unwillingness to accept that the world we see is all there is. This mindset has been a double-edged sword. It fuels our greatest achievements and our wildest fantasies alike. The same restless spirit that imagines magical portals also drives us to invent, to explore, and to push every boundary we encounter. Perhaps portals, real or imagined, are an expression of the human soul's refusal to be contained. We are always seeking more knowledge, more adventure, more meaning. A secret door is a perfect symbol of that quest. There's always the hope that just one step beyond the known lies something extraordinary that will transform our understanding of life. There is also a deeper spiritual yearning tied up in these tales of passage. Often, the world beyond the portal is not just different, it is better, purer, or more meaningful. Ancient heroes entered mystical gateways, searching for paradise, or for loved ones passed away, or for answers the ordinary world could not provide. This hints at a fundamental hope, that beyond the visible world lies something greater. The concept of a heavenly realm, an afterlife, or a utopia just out of reach might be humanity's way of expressing the same desire that portals in fiction do. A belief that beyond the mundane there is a place where all that is broken can be made whole. Even in play and daydreams, we create portals of the mind. A child draws a door on a wall with chalk and pretends it opens into a castle in the clouds. A simple cardboard box becomes a spaceship cockpit, ready to launch to distant galaxies. With a blanket and some chairs, kids fashion hidden forts that feel cut off from the real world. These games may seem trivial, but they reveal something profound about us. From our earliest years, we delight in the idea that there might be a secret way out of the ordinary and into the extraordinary. As we grow older, our imaginations find more subtle portals. We lose ourselves in books and films, transported by the stories unfolding in our minds. A compelling novel can make us forget the room we sit in, carrying us to a distant planet or a fantastical kingdom for hours at a time. Music and art can have a similar effect, opening doorways of emotion and memory that take us far from the present moment. In a very real sense, our creative pursuits are all about opening portals, not physical tunnels in space-time, but gateways in our minds that let us experience other places, times, and perspectives. Picture a child at bedtime, hiding under the blankets with a flashlight and a book of fairy tales. As she turns the pages, she imagines a door in her closet that maybe, just maybe, leads to a secret wonderland. In her mind, she can almost see it, a faint glow outlining the closet doorframe, a whisper of another world calling to her. For a while, the little room around her fades, and she is far away, exploring enchanted forests with talking animals. That ordinary closet has become a portal in her imagination, carrying her beyond the limits of her home and into a place of dreams. Even after the light is out, she falls asleep with the hope that someday, somehow, such a doorway might open for real. Beyond escape and hope, there is the simple thrill of the unknown. To step through a portal is to embrace mystery. We are drawn to the very idea of not knowing what lies ahead, of testing our courage in strange new realities. A hidden doorway presents a challenge. Will we dare to step through? That moment of anticipation, standing on the threshold, is a powerful spark to the human imagination. It combines excitement with a touch of fear, the exact mix that often makes us feel most alive. You can see echoes of this impulse when explorers venture into uncharted lands, or when someone climbs a mountain just to see what's on the other side. The portal is the ultimate version of that leap into the unknown. This deep-seated longing has not only spawned stories, it has driven real-world exploration and innovation. Our ancestors trekked into unknown lands, fueled by the hope of discovering something wondrous. In more recent times, that same spirit carried humans off the planet entirely. We built rockets to take us to the moon and sent robotic envoys to Mars and the outer planets. Scientists and engineers strive to push beyond Earth because we feel compelled to see what's out there. The idea of a cosmic shortcut, like a wormhole, inspires researchers to ponder if such things could ever be made real. The fantasy of portals reflects an underlying impulse that has always propelled humanity forward. The refusal to be contained, the desire to find a way to whatever lies beyond the horizon, or beyond the stars. Our fascination with portals is ultimately a reflection of our own dreams and drives. We carry that desire for the unknown inside us, always wondering what it would be like to actually go through such a gateway. What if one day the fanciful became real? If we stood before an open wormhole? The thought alone stirs both wonder and anxiety at once. Traveling through a doorway in space-time would not be an ordinary journey at all. So what might it actually be like to journey through a wormhole? We have imagined it for so long, yet the reality would likely surpass our wildest dreams or fears. We can try to picture it. A traveler stands before the mysterious portal, a shimmering distortion in space, a hole seemingly cut out of the fabric of reality. On this side, familiar stars and the warmth of home lie behind. On the other side, who knows? To step through that opening is to agree to leave everything you know in a single, breathtaking leap. Imagine that moment of decision as the traveler reaches out a hand and moves forward. The surface of the wormhole might shimmer like liquid glass or ripple like a pool of water. Crossing its threshold, our traveler might feel gravity shift strangely or a sudden weightlessness. There could be a brief sensation of falling or of being stretched and compressed at the same time as space twists around them. Or perhaps it would all happen in an instant with a flash, and they find themselves already through, heart pounding with exhilaration and relief. If the wormhole has an interior passage, perhaps the traveller would witness marvels as they move through it. They might see light bending in surreal patterns, stars and galaxies smeared into streaks of colour as though painted across a tunnel wall. Direction itself might lose meaning inside the tunnel. Without a normal up or down, they could feel as if they're floating freely in a void between realities. Sound might not carry normally. It could be eerily silent or filled with a deep, humming vibration from the energy holding the tunnel open. Time itself might feel strange inside. Seconds could stretch out, or whole hours might pass in a blink as the normal rules of time and space lose their grip. Then comes the other side, the emergence. In a heartbeat, our traveller could find themselves under an alien sky. Perhaps they arrive on a distant planet, orbiting a foreign sun, with unfamiliar constellations glittering above. The sky might have a different tint, say a pale orange or purple cast by that star's light, and maybe 2 moons hang low on the horizon. Imagine stepping out of the wormhole onto ground that no human has ever trod, breathing air with strange fragrances, seeing plants or landscapes that evolved under a different sun. The sense of awe would be overwhelming. In the span of a moment, they have crossed a cosmic ocean that would have taken millennia to traverse by ordinary means. But what of time? Wormholes, according to theory, do not just bend space. They can bend time as well. Our traveller might step through and find not only a different place, but a different era awaiting them. It's conceivable they could enter in 1 decade and emerge 100 years later, effectively leaping a century in a single stride. The journey might have catapulted them far into the future, or perhaps into the distant past. It all depends on the peculiarities of how the wormhole's ends are moving or positioned. Perhaps to the traveller the trip felt instantaneous, yet when they radio back home, they learn that years or decades have elapsed during that blink of an eye. This kind of time twisting is not just science fiction speculation. It is a real consequence scientists have pondered. And what of the way back? For any bold explorer stepping through a wormhole, the thought of returning home might be fraught with uncertainty. The wormhole that delivered them might vanish, sealing itself behind them like a door that locks shut. If time has shifted, they might return to find home drastically changed. One old folktale tells of a man who spent what felt like 3 days in a magical realm, only to find 300 years had passed at home. In some legends, those who ventured into other realms could never truly return to the life they left. And even if the portal did reopen, the traveller could discover that they themselves have been transformed by the journey, no longer at home in the world they left behind. A wormhole voyage might carry a similar bittersweet price. There is even the possibility that a wormhole might not lead to our universe at all, but to a completely different reality. Some theories of physics entertain the idea of parallel universes, entire realms with separate histories and perhaps different laws of nature. A wormhole could, in principle, be a tunnel connecting not 2 distant corners of the same cosmos, but 2 different universes entirely. What would it mean to step out into a parallel world? The traveller might find a place both familiar and bizarre, where even the stars in the sky were alien. Such a journey would raise questions perhaps even greater than travelling across space or time. It would be a voyage into a fundamentally unknown existence, a true beyond. Yet the idea of a journey without end is not only a warning, it can also be a promise of endless discovery. If wormholes truly network the cosmos, A daring soul might roam from one cosmic tunnel to another, never settling, always finding a new horizon beyond the next portal. Each wormhole could open onto a different corner of the universe, or perhaps into entirely different universes altogether. Such a traveler would become a wanderer of infinite realms, their voyage limited only by how far their courage and curiosity could take them. This is the ultimate adventure, a journey that literally has no end, with always one more world to step into beyond the last. For now, such scenarios remain in the realm of imagination. No human has yet made such a journey. Wormholes are still theoretical gateways, tantalizing but unproven. And yet, we cannot help but wonder, what if one day we could not only find a wormhole, but actually create or open one at will? With that prospect comes both exquisite dreams and profound dangers for our civilization. With this in mind, we turn to consider what wonders and perils might unfold if humanity ever gained the power to open a wormhole for real. If humanity could one day open a wormhole, it would mark a turning point in our history, as profound as the discovery of fire or the splitting of the atom. Such a feat would mean we had mastered a key to the cosmos that was once only dreamed of in myths and science fiction. For ages, we have gazed at distant stars and felt the sting of their unreachable distance. Opening a wormhole would instantly erase that distance, making the farthest reaches of space as close as the next room. In one stroke, the universe would feel far smaller and more accessible than ever before. The dreams that come with such an achievement are dazzling. We could explore distant star systems, not in generations or centuries of travel, but in the span of an afternoon. Planets orbiting other suns, which today are mere specks in our telescopes, could be just a step away through a portal. We might establish colonies on far-off worlds without the need for multi-year voyages. Imagine being able to attend a meeting on Earth in the morning and watch the sunset from an exoplanet by evening. Wormholes could turn us into a truly interstellar species, fulfilling the age-old human desire to wander among the stars. Such portals might also solve problems that have plagued humanity for centuries. Resources could be transported from one world to another, alleviating shortages and expanding our access to materials and energy. If Earth faced an extinction-level threat, say, an asteroid impact or a climate catastrophe, a network of wormholes might allow large populations to evacuate to safety on other planets. Medical knowledge and technology could be shared instantly between colonies light years apart. The barriers of distance and time that have long constrained us would crumble, potentially ushering in a golden age of prosperity and collaboration on a galactic scale. We can imagine a future scenario to glimpse these possibilities. Picture a time when Earth faces a grave crisis, perhaps an environmental collapse or a spreading pandemic. Scientists have by then mastered the art of opening wormholes. In humanity's darkest hour, they activate a portal as a last refuge. A great shimmering gateway stands in a launch bay, and families step through carrying children and hopes, emerging light years away on a new world under a friendly sun. In that moment, the wormhole is nothing short of salvation, a bridge carrying people from certain doom to a second chance. This is the kind of dream that makes the pursuit of wormhole technology so enticing. The idea that we could, literally, open a door to a better future when one is desperately needed. The scientific knowledge gained would be enormous as well. We could study black holes, nebulae, or even other galaxies up close by placing a wormhole doorway right where we want it. If there are other intelligent beings out there, Wormholes might enable contact and exchange that were previously impossible across the abyss of space. We might finally get answers to some of humanity's biggest questions. For example, could we learn once and for all if we are truly alone in the universe and discover what the cosmos is like beyond our tiny corner of it? A wormhole could be not just a bridge for travel, but a bridge for communication and understanding on a cosmic scale. Even the boundaries of time could be challenged. If wormholes allowed it, we might imagine stepping into our own past or peeking at the future. Such a power could let us witness historical events firsthand or see what becomes of our descendants. The chance to say goodbye to a loved one long past, or to avert a tragedy by visiting a key moment in history, is a bittersweet fantasy that wormholes tantalize us with. Of course, the paradoxes and perils of time travel are immense, but as a dream, it remains one of the most profound lures of a cosmic doorway. Yet alongside these dreams comes a shadow of potential danger. Just as opening a wormhole might unite far-flung worlds, it could also unleash forces or consequences we are ill-prepared for. Human history teaches us that powerful new abilities often carry risks we didn't anticipate. The first astronauts opening the way to space also brought back worries of contamination or unforeseen hazards. Splitting the atom gave us light and power, but also the spectre of nuclear destruction. Opening a wormhole would be no different. Its use could bring unintended and possibly uncontrollable outcomes. One concern is sheer instability. A wormhole is not a door carved in wood. It is a dynamic structure held open by extreme forces. If something went wrong, a man-made wormhole might collapse violently. The energy released could be catastrophic, perhaps spawning a burst of radiation or even a black hole. Opening spacetime is not like opening a window. The fabric of the universe might react in ways we cannot fully predict. An attempt to create a portal could, in the worst case, tear something we don't know how to mend. Even if the wormhole itself behaved, there is the question of what lies on the other side. When we open a door, we are also inviting whatever is beyond it to cross the threshold. If a wormhole connected us to a distant part of the galaxy, who is to say something dangerous might not come through unannounced? It could be harmful microbes from an alien ecosystem, against which we have no defenses. It might also be something non-living, yet lethal. Perhaps a blast of intense radiation from a star, or a stream of exotic particles flung out of the tunnel. Or it could be larger threats, a predatory life form, or even an intelligent adversary. By creating a bridge to another world, we make a two-way passage, and that means accepting the risk that we might not be the only ones to use it. There are also dangers in how we ourselves might use this power. A wormhole could become the ultimate weapon if turned to violent ends. Just imagine. The ability to send a fleet or a missile instantly anywhere could upend the balance of power on Earth. No place would be remote enough to be safe. No warning system could detect an attack that arrives in the blink of an eye. A nation or group that controlled a wormhole might dominate all others by the mere threat of striking from nowhere. And even without malice, accidents or negligence could turn a miraculous tool into a catastrophe. The responsibility that comes with opening space-time is immense, and human fallibility would make it a constant challenge to manage safely. Time travel introduces its own thorny issues. If wormholes allowed movement through time, it would open a bewildering array of problems. The ability to send people or information to the past or future could wreak havoc with history and causality. A traveler could, intentionally or not, change a past event, the classic grandfather paradox, potentially erasing the future they came from. Even knowledge of future events delivered to the present could distort decisions in dangerous ways. We would face ethical dilemmas never encountered before. Should anyone be allowed to tamper with the timeline? Could the flow of history be protected if an open wormhole links today with tomorrow or yesterday? Humanity might find itself overwhelmed by the paradoxes and moral questions such power presents. Even the social fabric of humanity could be strained by such sudden freedom. If distance ceased to be a barrier, nations and communities would no longer be separated by oceans or light years. While this could foster unity, it could also bring culture shock and conflict as worlds collide overnight. Economies might be upended when goods and people can appear anywhere instantly. Our very sense of home and belonging might change when anywhere else can be reached on a whim. The wormhole, as wonderful as it would be, could challenge the way we organize our civilization in ways we cannot foresee. Clearly, the power to open a wormhole would be both blessing and burden. It holds the promise of extraordinary advancement and the peril of equally extraordinary disaster. As with any great power, the outcome would depend on how wisely it is used, and perhaps on factors beyond our control. For even if we yearn to wield this power, the universe itself might have the final say. Wormholes, by their very nature, could be exceptionally fragile phenomena. The next question is whether such bridges could ever remain open long enough to serve our dreams, or whether they are destined to flicker out as quickly as they form. All evidence so far suggests that wormholes, if they exist at all, are incredibly delicate structures. Theoretical physicists have long pointed out that a wormhole might collapse in the barest fraction of a second. Like a soap bubble that forms and pops almost in the same instant, a natural wormhole could wink out before anything, even light, could traverse it. The bridges, imagined by Einstein and Rosen, were found to pinch themselves off so quickly that no traveller could ever cross from one end to the other. In this sense, wormholes might be only marginally less fleeting than a flash of lightning or a spark from a fire, a brief connection that vanishes as soon as it appears. The reason lies in the tremendous forces at play. Under normal circumstances, gravity works to shut a wormhole almost as fast as it opens, drawing the tunnel closed. To hold a wormhole open, physics tells us we would need something extraordinary, so-called exotic matter with negative energy. This is not the kind of matter we find in daily life. It's a hypothetical substance that could push space apart instead of pulling it together. Without it, any wormhole we manage to create or encounter would likely snap shut instantaneously. With it, in theory, the tunnel might be propped open, but generating or gathering such exotic energy is a feat far beyond our current technology. Some scientists speculate that wormholes flicker in and out of existence constantly at the tiniest scales. In quantum physics, space itself might be seething with quantum foam, a froth of tiny wormholes forming and vanishing almost instantly. These microscopic bridges would be far too small for even an atom to pass through, and they wink out as soon as they appear. If this is true, then wormholes could be a fundamental but hidden feature of the cosmos, forever beyond our direct reach unless we find a way to capture one and enlarge it, like stabilizing a delicate bubble before it bursts. So far, none of these minute bridges has ever been observed directly, underscoring just how elusive and fleeting this phenomenon is. Even on a larger scale, any traversable wormhole would likely require constant care to remain open. The slightest disturbance, a burst of energy, the passage of a ship, even light itself, could destabilize the passage. In a sense, a wormhole might be its own worst enemy. As soon as anything tries to travel through, the act of traveling could start to tear the bridge apart. To maintain it, enormous control might be needed, feeding it with exotic energy like buttresses to support an arch. It would be akin to holding open a hole in the ocean while water pressures push to close it. The moment you stop pushing back, the opening collapses. Absent continuous support, the tunnel would fold back into ordinary space in the blink of an eye, stranding whatever began to cross it. It is perhaps no surprise, then, that we have never seen an obvious wormhole out in space. If any formed naturally in the cosmos, they might flicker out too fast, or be hidden inside extreme environments like black holes. Astronomers have not found any telltale signs, no mysterious gateways or inexplicable shortcuts that objects seem to be taking. If advanced civilizations exist, perhaps they have ways to stabilize wormholes. But if so, we have yet to detect their handiwork. For now, wormholes remain theoretical, evading our telescopes and experiments, as ephemeral as dreams. Interestingly, the pursuit of wormholes has already taught us a great deal about physics. To even imagine these tunnels, scientists have had to push the limits of general relativity and quantum theory. Wormholes sit at the intersection of these two great pillars of modern physics, gravity and the subatomic world, an intersection we still struggle to fully comprehend. By probing whether wormholes can exist, physicists end up exploring deep questions about the nature of space, time, and energy. In trying to figure out how a wormhole might work, or why it might not, we are essentially doing thought experiments on the universe's most fundamental laws. In this way, the concept of wormholes acts as a catalyst for scientific discovery, driving us to seek a unified understanding of reality. Wormholes might forever be fragile bridges, tantalizing in theory, but vanishingly difficult in reality. Even if they remain a mathematical possibility never realized, the quest to understand them has already enriched our view of the universe. In grappling with wormholes, we are forced to rethink space, time, and energy at the most profound level. The journey of understanding continues, fueled by curiosity and the faint hope that one day these cosmic doorways could become more than theoretical. For now, the wormhole remains a powerful symbol of the mysteries still out there in the dark, and of our human desire to reach through the unknown and find what lies beyond. In the quiet realm of theoretical physics, the journey to understanding wormholes often begins not with roaring rockets or fantastical starships, but with equations on a chalkboard. Late at night, under the glow of a single lamp, a physicist traces symbols and numbers that dance across the board. These equations are the language of the universe, describing how space curves and time bends. Among these abstract lines, a peculiar solution emerges, a mathematical whisper of a doorway hidden in the fabric of spacetime. It's a strange, elegant possibility that hints at paths through the cosmos where none should exist. The idea of a cosmic tunnel was born from Einstein's own equations of gravity. Just after Einstein formulated general relativity, a little-known Austrian physicist named Ludwig Flamm found something intriguing lurking in the math. In 1916, only months after the concept of a black hole was first theorized, Flamm noticed that the equations had more than one solution. Besides the path that describes a collapsed star, a black hole, there was a mirror image solution, like a secret backdoor in space-time. Decades later, Albert Einstein himself, together with Nathan Rosen, studied this idea further. In 1935, they described what we now call the Einstein-Rosen bridge, a hypothetical tunnel connecting two distant points, born from the equations of gravity. At first, this Einstein-Rosen bridge seemed to offer a shortcut through space and time. On paper, one could fall into a black hole in one region and perhaps emerge from a white hole somewhere else, as if the universe had a hidden escape hatch. To the mathematicians, it was as if space-time had folded in on itself, allowing two separate places to touch. However, As they probed deeper, they realized this bridge was a fleeting one. The tunnel pinched off too quickly. It was as if the universe allowed a door to crack open for a moment, then slammed it shut before anything could pass through. Wormholes, it seemed, might exist in theory, but nature guarded them tightly. Yet the very presence of these solutions in Einstein's theory was enough to captivate physicists' imaginations. The mathematics did not outright forbid such doorways. It simply showed they would be unstable. This thin ray of possibility was tantalizing. Over the years, scientists kept returning to it, like a half-remembered melody that promises some deeper truth. The term wormhole was coined in the 1950s by physicist John Wheeler, evoking the image of a tiny creature burrowing a tunnel through an apple. In Wheeler's vision, our universe was the apple, and the wormhole was the shortcut through its core, a clever illustration of a complex idea. It was a poetic leap of language, perfectly capturing the essence of these hypothetical passages. One can almost picture those early researchers in a quiet office, pencil in hand, marveling at what their equations revealed. To them, it must have felt like uncovering a secret doorway drawn into the fabric of reality. The math was telling them a fantastical story, one that hinted they might have found something truly profound. In that moment, the line between calculation and inspiration blurred, and a new chapter of cosmic possibility opened before their eyes. As the decades went on, researchers asked a bold question. Could a wormhole be held open? If the Einstein-Rosen bridge naturally collapses too quickly, perhaps there is a way to prop it open, to prevent the cosmic door from closing. The equations hinted at an answer, but it was an exotic one. To keep a wormhole's throat agape, one would need something extraordinary. Matter with negative energy, a kind of anti-gravity pressure to hold the tunnel's walls apart. In ordinary experience, such stuff doesn't exist. All mass we know of attracts. None repels in the way required. But quantum physics, strange and subtle, offers a glimmer of this exotic possibility. In the microscopic world, even empty space isn't truly empty. Particles flicker in and out of existence, and with them, fleeting negative energies can appear. Physicists realize that the fabric of space on tiny scales, the quantum foam, might harbor these minute, momentary traces of negative energy. It wasn't much, but it was enough to suggest that the laws of physics permit this weird ingredient, at least in principle. But quantum physics, strange and subtle, offers a glimmer of this exotic possibility. In the microscopic world, even empty space isn't truly empty. Particles flicker in and out of existence, and with them, fleeting negative energies can appear. Physicists realize that the fabric of space on tiny scales, the quantum foam, might harbor these minute, momentary traces of negative energy. It wasn't much, but it was enough to suggest that the laws of physics permit this weird ingredient, at least in principle. This revelation was profound. It meant the theoretical recipe for a wormhole wasn't entirely forbidden. If we could thread enough negative energy into a collapsing tunnel, we might hold it open. In the late 1980s, renowned physicist Kip Thorne and his colleagues took these ideas and worked out detailed designs for traversable wormholes. They treated it almost like an engineering problem. What kind of conditions, what amount of negative energy would you need to let a person travel safely through a wormhole? The numbers they found were daunting. The amount of negative energy was enormous, but not infinite. The exercise itself was a testament to human curiosity, using pure mathematics to test the limits of the possible. All the while, wormholes remained firmly in the realm of theory. No telescope or experiment had ever seen evidence of one. Still, the equations were like a map, marking a destination that might or might not exist. In those equations, wormholes appeared as peculiar solutions, much like how black holes were once just peculiar solutions before we confirmed they were real. It made scientists wonder, could wormholes too be more than mathematical ghosts? The math suggested that if the universe had certain conditions, a twist here, a squeeze there, a tunnel could form. Perhaps in the furious mixing of energy right after the Big Bang, or in the hearts of collapsing stars with some extraordinary twist of physics, nature might have crafted a wormhole or two. On the smallest scales, some theories even imagine a roiling sea of tiny wormholes. John Wheeler's idea of spacetime foam pictures the fabric of the cosmos at the Planck scale, the very tiniest scale imaginable, as jittery and turbulent. Space and time might be constantly warping, forming pinprick wormholes that blink in and out of being in trillionths of a second. These would be far too small for a person, or even an atom, to traverse, and they'd vanish almost as soon as they appeared. But their existence would mean wormholes are not just a figment of our equations. They could be a fundamental part of how space-time operates at the quantum level. It's a breathtaking concept, that the universe, at its most microscopic, is threaded with countless miniature tunnels, a hidden network beneath the smooth surface of reality we perceive. Through mathematics, we thus glimpse a universe that permits fantastical things. Equations have a way of revealing truths that our senses can't. They tell us that under the right conditions, space and time might bend to the point of looping back on themselves, connecting distant stars or even distant eras. To solve these equations is to peer into the universe's secret choreography. It is an almost meditative act, following the logic of symbols to places human eyes have never seen. And in that meditative journey, wormholes appear like a promise, a whisper that says, there is more to reality than what we see. From scribbles on a chalkboard to published papers filled with dense mathematics, the concept of wormholes moved into the scientific mainstream as a serious, if speculative, topic. Each equation solved, each theoretical paper, has been a step further down this rabbit hole of the cosmos. The math of wormholes, intricate and abstruse, became a beacon in the search for a deeper understanding of space and time. And intriguingly, those same equations that opened the door to wormholes also pointed to the real cosmic phenomena that might bring us closest to them: black holes. After all, it was in studying black holes that the first wormhole popped out of the equations. These dark, massive objects seem to be nature's way of bending space-time to extremes. If any place in the universe could hide a pathway to elsewhere, it would be in the grip of such intense gravity. And so, our journey moves from the realm of pure mathematics to the realm of massive stars and the darkness they leave behind, toward the black holes themselves, cosmic giants that might just hold the key to unlocking wormholes in reality. Black holes are among the most mysterious and fearsome objects in the universe. They begin life as giant stars, many times the mass of our sun, that burn brightly for millions of years. But even stars meet their end. When a very massive star exhausts its fuel, it can no longer hold itself up against the relentless pull of gravity. The star's core collapses in on itself in a cataclysmic implosion. In that moment, all the star's remaining mass is crushed into an unimaginably small space, and a black hole is born. The light of the star disappears, replaced by a different kind of presence, a region of space so gravitationally intense that nothing, not even light, can escape its grasp. To an outside observer, A black hole is essentially a one-way door. Anything can enter, but nothing returns. The boundary of no return is called the event horizon, an invisible sphere around the collapsed star. Cross that boundary, and the path forward inevitably leads inward, deeper into the blackness. For decades, black holes were purely theoretical, a strange prediction of Einstein's equations that many scientists doubted could be real. Slowly, evidence mounted. Stars orbiting an unseen mass, X-rays from gas heated to extreme temperatures as it swirled into an invisible abyss. By now, black holes have moved from theory to fact. In recent years, we even captured an image of one, a glowing ring of hot gas silhouetting a dark center, providing the first direct visual evidence of a black hole's existence. These dark giants have become a centerpiece of modern astronomy, confirmation that nature truly creates these cosmic traps. Imagine drifting closer to one of these cosmic abysses, in a spaceship, or perhaps just in your mind's eye. As you approach the event horizon, starlight around you bends and warps into surreal halos. Time itself seems to slow down. There is no sound, just the silent pull of the black hole drawing you in. It is both eerie and mesmerizing, a frontier where the normal rules of reality begin to melt away. Yet, in the shadow of their discovery lies a further tantalizing question. Could black holes also be gateways? The mathematics of general relativity first hinted at this possibility. The very solution that describes a black hole also suggests a mirror solution, a white hole. A white hole is essentially the reverse of a black hole. Nothing can enter it. Everything can only burst out. In theory, a black hole could be connected to a white hole, forming a tunnel through space-time. This is the Einstein-Rosen bridge we encountered earlier. If you fell into a black hole in one universe, you might emerge from a white hole in another universe. It sounds like science fiction. And indeed, as far as anyone can tell, it might be. In reality, a black hole that forms from a dying star likely doesn't produce a white hole elsewhere. The connection seems to be broken by the very act of stellar collapse. The bridge closes almost as soon as it forms. Still, the idea refuses to fade away. Physicists have explored other kinds of black holes in their equations, ones that spin or carry electric charge. These more complex solutions reveal that rotating or charged black holes have richer inner structures. If one could travel into a rotating black hole, the math implies there might be a way through without hitting an infinite crunch at the center. Instead of a dead-end singularity, a fast-spinning black hole might contain pathways to other regions of space-time, or even other universes. Some interpretations suggest that through the center of a Kerr black hole, one might avoid destruction and slip out into a different time or place, essentially using the black hole as a wormhole. However, there's a big catch. These pathways are probably not stable. The slightest disturbance could seal them off, or turn them into impassable mazes of curved space. And any real traveler would still face lethal conditions, intense radiation, tidal forces that stretch and compress anything into strands of atoms. So while the equations tease us with exotic possibilities, nature might not grant safe passage this way. The concept of a white hole, too, remains speculative. It appears naturally in the math, but unlike black holes, we have never seen a hint of one in reality. If a black hole were ever part of a wormhole, the white hole would be the far end of that tunnel, a bright fountain of matter and light, spewing out into some other place. We don't observe anything like that in our universe. If white holes do exist, they might have been objects of the very early universe, or perhaps they exist in some separate cosmic region entirely. In our day-to-day cosmos, black holes reign alone, with no visible counterpart. Another thread tying black holes to wormholes comes from the world of quantum physics. In recent years, a bold idea emerged, encapsulated in the phrase ER is EPR. This conjecture, by physicists Leonard Susskind and Juan Maldacena, suggests that an Einstein-Rosen bridge, ER, might be fundamentally related to quantum entanglement. EPR refers to Einstein-Podolsky-Rosen, a famous quantum thought experiment. In simple terms, they speculated that if two particles are quantum entangled, perhaps they are connected by a tiny wormhole. Extending this idea, two entangled black holes could conceivably share a connection through a wormhole. If true, this would marry the strange world of quantum mechanics with the cosmic geometry of spacetime in a startling way. Imagine, you create two black holes in a lab, a far-fetched scenario itself, and entangle them somehow, then pull them far apart. According to ER equals EPR, those two black holes might be linked by an invisible thread, a wormhole, that reflects their entangled nature. This idea is still very much theoretical and not proven, but it illustrates how black holes sit at the crossroads of many deep questions. They might teach us not just about gravity, but also about the quantum fabric of reality. Black holes, therefore, serve as a natural testing ground for wormhole theories. They push physics to extremes, where space and time warp beyond the ordinary. In their presence, our intuition fails, and only careful calculations, and someday perhaps bold observations, can guide us. Wormholes may or may not exist in the wild cosmos, but if they do, black holes are likely involved, either as the very structure of a wormhole's mouth, or as the inspiration that led us to conceive of wormholes in the first place. Every time we peer at a black hole, detect its gravitational waves as it merges with another, or map the stars orbiting the invisible monster at our galaxy's core, we are also indirectly probing ideas related to wormholes. We're observing what space-time does under almost unimaginably extreme conditions. And perhaps, hidden in those extreme corners, the universe has left a few surprises for us. After all, what truly lies inside a black hole? That question brings us face to face with one of the greatest mysteries in physics, the singularity. This is the point, deep in the black hole's core, where density and gravity might reach infinite values in the equations. Our current understanding breaks down there. It's a tantalizing thought that at this central point, this singularity, could lie the key to wormholes, or perhaps something even stranger. To find out, we must confront the singularity itself, and venture as far into the heart of gravity as physics will allow. At the center of a black hole lies the unknown. We call it a singularity, a point or region, where our theories predict that gravity becomes infinite and space-time curvature grows without bound. It's a place where the familiar laws of physics no longer make sense. All the mass of a collapsing star, in theory, gets squeezed into an infinitely small volume. What does that even mean? In truth, no one knows. The equations give us a result that seems absurd, a sign that we've pushed them beyond their limits. At the singularity, nature hides its secrets behind a veil our science cannot yet lift. In a way, the singularity is a shadow cast by our ignorance. It marks the boundary of where our understanding ends. As we approach it mathematically, quantities like density and curvature head toward infinity, and our equations simply break down. Physicists generally believe that infinite values signal that the theory we're using, general relativity alone, is incomplete. To really grasp what happens at a singularity, we likely need a new theory, one that blends gravity with quantum mechanics. This long-sought quantum gravity might soften the sharp edges of the singularity, replacing the infinite chaos with something we can make sense of. Until we have that theory, the singularity remains a mystery at the heart of every black hole, an abyss where our certainties end. If we could send an indestructible probe into a black hole, what would it see as it neared the singularity? The truth is, even our best guesses might be wildly off. Some think the probe would be stretched and squeezed by infinite gravity. Others imagine it might slip through a fissure into another realm. Without a theory to guide us or an experiment to confirm, we're left with speculation. At the doorstep of the singularity, science turns into a kind of guided dreaming, constrained only by the requirement that we obey what we do know of physics. It's fascinating to consider that a singularity might not be the definitive end of the line. Some physicists have imagined scenarios where what looks like a singularity is actually a bridge to something else. One idea is that perhaps the matter collapsing into a black hole doesn't vanish, but gets funneled through and out a back door. In such speculative models, a black hole could be connected to a new region of spacetime, or even another universe, through its singularity. In other words, the singularity might be less like a brick wall and more like a tunnel entrance, albeit a very violent and one-way tunnel. These ideas are highly theoretical, but they stir the imagination. Could the crushing gravity at a black hole's core actually be punching a hole in the fabric of reality? There are also theories that attempt to eliminate singularities altogether by changing the rules of gravity. For instance, in some quantum gravity models or alternative theories like loop quantum gravity, when a star collapses, the collapse might reach an ultra-dense state, but then rebound instead of forming a true singularity. The result could be a bounce. The black hole becomes a passage to an expanding space on the other side, rather than ending in a point of infinite density. Such scenarios replace the fatal crunch with a kind of cosmic trapdoor. Some even speculate that perhaps our own Big Bang was spawned from such a bounce, the other end of a black hole from a previous universe. It's a mind-bending thought. Every black hole could be a Big Bang for a new cosmos, the death of a star giving birth to a baby universe through the gateway of a wormhole-like bridge. So far, these ideas remain in the realm of theory, without evidence, but they offer a hint of what might lie beyond the singularity, if our equations can be trusted into those extremes. We must also reckon with the fact that nature keeps singularities well hidden. According to the cosmic censorship conjecture, a hypothesis first proposed by physicist Roger Penrose, every singularity in our universe comes cloaked by an event horizon, a veil ensuring that the monster at the center is never exposed to the outside world. This principle is a kind of safety net in physics. It says that the weirdness at a singularity can't influence distant regions because it's always sealed inside a black hole. To date, every black hole we know respects this rule. None show any signs of exposing a naked singularity. But theoretical physicists love to ask, what if? What if a singularity could be laid bare, uncovered by any horizon? Such a naked singularity is a terrifying prospect in some ways. Physics as we know it might break down not just in a hidden corner, but out in the open for all to see. Some have speculated that a naked singularity might behave like a wild fountain of energy, or even allow peculiar violations of cause and effect, time travel shenanigans, for example? Could a naked singularity also be a doorway of sorts? It's an open question, one that ventures deep into speculative territory. So far, nature seems to play it safe, hiding singularities within black holes. But the very idea that one could be exposed continues to tantalize scientists. Standing outside a black hole, we can only imagine what happens in those final moments of collapse. All pathways lead to that central point where the known laws of physics falter. Is it a true dead end? A point where everything is destroyed utterly? Or is it a bend in the road, curving into another realm of space and time? Wormholes often come into the discussion here, because a wormhole could be one resolution to the puzzle, an escape route of sorts, from the otherwise terminal crunch of a singularity. Perhaps under the right conditions, the collapsing star's core doesn't obliterate information and matter, but shunts it through a wormhole tunnel. From the outside, we'd still see a black hole, but beyond the horizon, travelers, hypothetical ones, as no actual astronaut could survive this, might ride the collapse through a tunnel and out elsewhere. It sounds fantastical, and indeed it is highly speculative. But without hard facts, we are free to wonder and weave possibilities. At this juncture, our journey takes us to the edge of knowledge. The singularity is the ultimate unknown, the place where the tapestry of physics unravels. It's a realm where science meets philosophy, where questions about determinism, reality, and even the origin of the universe all swirl together. We often say that singularities are where God divides by zero, a humorous way to acknowledge that our mathematics simply breaks. And yet, within that breakdown may hide the clues to a deeper truth. Perhaps one day, if we develop a true quantum theory of gravity, we will find that singularities aren't singular at all. Maybe they blossom into something unexpected, new structures or gateways that we can scarcely dream of now. Until then, singularities remain as they have always been. Silent, dark enigmas. They challenge us to push physics further, to find out what reality does when pushed to its absolute limit. And as we prepare to move on from the depths of black holes and their hidden hearts, we turn our eyes to the broader stage of the cosmos once more. Could there be wormholes out there in the wild, lurking among the stars? That is the next question on our journey. The universe is vast and full of wonders. Could wormholes be among them, quietly hiding in plain sight? So far, we have not caught one in a telescope's gaze or on any detector. But scientists have not given up the search. If wormholes exist naturally, they might masquerade as other things, making them hard to recognize. One possibility is that a wormhole's mouth could look a lot like a black hole from the outside. After all, both involve intense gravity that can bend light. A wormhole entrance might just appear as a dark, heavy mass pulling on nearby stars, just as a black hole does. We could be observing a wormhole right now, mistaken as an ordinary black hole, and we wouldn't know without closer investigation. Astronomers have pondered what signs might betray a hidden wormhole. One clue could come from the way light bends around a massive object, a phenomenon known as gravitational lensing. A wormhole might lens light in unusual ways. Imagine observing a distant star and seeing not one, but two or more images of it, distorted and strangely arranged. A black hole can do that, but a wormhole might create a distinctive pattern, perhaps splitting or shifting the images in ways that don't quite match a black hole's signature. Researchers have proposed searching sky surveys for such odd lensing patterns as a way to hunt for wormholes. It's a bit like looking for a mirage in the starlight, subtle and tricky, but not impossible. Or perhaps the evidence will come from the motion of stars. Consider a star that seems to be orbiting empty space, circling a point where no visible object resides. To an observer, it would be a perplexing dance. We might calculate that something massive must be there, exerting a gravitational pull, yet telescopes see nothing. Could it be that the star is feeling the gravity of a wormhole's mouth, a hidden mass masquerading as a void? It's a daring thought, and so far we haven't found such a situation. But if we ever did, it would be a strong hint that a cosmic tunnel lies in hiding. Another hint might come from the dance of stars and gas. In our own Milky Way galaxy, we've observed stars whipping around an invisible massive object at the center. That's how we confirmed the supermassive black hole, Sagittarius A. Now, a few scientists have speculated. What if that object isn't a plain black hole, but a wormhole? It's a far-fetched idea, and likely not the case, but it shows the kind of questions being asked. If Sagittarius A were a wormhole, and if something on the other side could influence it, we might see slight deviations in the orbits of those stars, tiny anomalies that wouldn't occur with a solitary black hole. Efforts are underway to measure those star orbits with incredible precision. If any odd deviations were found that defied the expectations of a black hole's gravity, they would spark intense interest, though many explanations besides a wormhole would have to be ruled out. So far, observations at the galactic center fit well with a normal black hole. No exotic deviations have been spotted. But the fact that we can even pose the question is a testament to human curiosity. Either way, pushing our observations to such precision expands our understanding of the cosmos. Wormholes might also hide in more subtle ways. Some theories suggest that the early universe could have made tiny wormholes spontaneously during the Big Bang, possibly stretching some to macroscopic size during the inflationary epoch. If so, there might be ancient wormholes drifting in intergalactic space, very hard to detect because they might not have any matter glowing around them. They'd be like ghost portals, influencing things only through gravity. A particle or light beam passing very near one might have its path slightly altered in a telltale way. Detecting that would be extraordinarily difficult, but not out of the question as our instruments improve. There's even speculation that such wormholes, if numerous enough, could contribute to the dark matter problem, the unseen mass whose gravity affects galaxies. Perhaps part of the missing mass in the cosmos is not exotic particles at all, but a plethora of tiny wormholes scattered throughout the universe. It's a highly speculative idea, and most scientists suspect dark matter is something else. Nevertheless, this kind of thinking shows how creative scientists have become when considering hidden cosmic phenomena. For now, every mysterious astronomical observation gets scrutinized for potential signs of the unexpected. A fast radio burst, a peculiar cosmic flash, an unexplained gravitational wave signal. Each new puzzle makes scientists wonder if we might have chanced upon evidence of something like a wormhole. Thus far, no such discovery has occurred. Each time, more mundane explanations have won out, and wormholes remain elusive. But that doesn't mean they're not there. It's a big universe, and we've charted only a tiny portion of it. Not too long ago, black holes themselves were purely theoretical. Many doubted we'd ever confirm one, and yet now they are firmly part of our cosmic landscape. In the same way, wormholes might one day move from speculation to observation. It could happen when we least expect it. A strange reading from a spacecraft or telescope that, after all other explanations are exhausted, points to a tunnel through space-time. Until then, the search continues, quietly and doggedly, as scientists keep their minds open to the wild possibilities that nature might be hiding. Thinking about wormholes hiding among the stars makes us realize something. Even if they are never found, the very act of searching expands our understanding. We learn more about black holes, galaxies, and the fabric of space in the process of looking for the extraordinary. The pursuit itself has value. It reminds us that the universe still holds many secrets, and that sometimes we have to look at things in a new light. Literally, in the case of gravitational lensing, to uncover hidden truths. In our quest to find wormholes, we sharpen our tools, refine our theories, and often discover other wonders along the way. The journey, as much as the destination, drives science forward. And as our journey through this story continues, we find ourselves drawn from the cold expanse of space back into the realm of human experience. It is there that the boundary between hard science and poetic imagination begins to blur. Our exploration is about to venture into that hazy intersection, where facts and dreams intermingle. Perhaps there, we will find new insights, not just about the cosmos, but about ourselves. From the very first time the term wormhole was whispered beyond academic circles, it captured the human imagination. Here was a concept born from rigorous science, Einstein's equations no less. Yet it felt as magical as any fairy tale door or enchanted portal. A tunnel through space and time, a bridge between distant worlds. It's the stuff of dreams. And so, wormholes quickly found a dual life, one in equations and journals, and another in our collective imagination. They've appeared in countless science fiction stories, films, and artworks, often depicted as swirling gateways in space. Through these cultural portrayals, wormholes have become a symbol of the possible, a metaphor for overcoming the vast distances that separate us from the stars, or even from each other in time. In this way, physics meets poetry. The hard calculations of general relativity give rise to something profoundly evocative, an idea that speaks to our deepest longings. Who hasn't looked up at the night sky and felt a pang of yearning to know what lies beyond, to visit those distant stars? Wormholes, as a concept, offer a whisper of a chance to fulfill that longing, to shortcut the impossible gulf. It's a scientific idea, yes, but it resonates like art. The language we use to describe it is rich with imagery. Scientists, normally so cautious, sometimes speak of wormholes in almost whimsical terms. One can sense the awe and wonder beneath the technical jargon. In discussing warp drives and wormholes, even a physicist's prose can bloom into something that sounds a bit like poetry. There is a kind of feedback loop between science and imagination when it comes to wormholes. The science gave us the concept. Then imagination took that concept and ran wild with it. Those imaginative explorations in novels and films, and yes, in our daydreams, in turn inspire new scientific questions. A researcher might admit that a childhood spent reading stories of interstellar voyages through wormholes led them to study astrophysics. Meanwhile, when science makes a new discovery or pens a new theory, storytellers seize it and weave new tales. The boundary between what is real and what is dreamed blurs, each influencing the other. Wormholes exemplify this beautifully. They exist in the realm of theory, but they feel almost tangible in our cultural imagination, as if one might lurk just beyond our reach. A notable real-world example of this interplay came when novelist and astronomer Carl Sagan set out to write about wormholes. He consulted physicist Kip Thorne to ensure that the wormhole in his story was as scientifically plausible as possible. The result was a work of fiction strengthened by real equations, and in turn, that collaboration sparked new academic discussion about the nature of time travel through wormholes. It was a case of imagination and science, actively inspiring one another. With wormholes, scientific discourse often opens up philosophical and even spiritual questions. If we could travel through time via a wormhole, what would that do to our understanding of cause and effect, of fate and free will? If wormholes connect distant parts of the universe, do they hint at a deeper connectivity in the cosmos, perhaps a cosmic web that binds everything? Such questions drift into the territory of metaphysics and meaning. It's here that the language of physics can sound like poetry, grappling with concepts that border on the mystical. We find scientists musing about whether spacetime has a kind of architecture that is labyrinthine, full of hidden passages. We hear metaphors and analogies invoked to capture what straight equations cannot fully convey to the layperson, or even to the scientists themselves. In trying to describe a wormhole, one almost inevitably reaches for imagery, because the literal truth is so staggering to consider. And of course, wormholes inspire that most human of qualities: hope. Hope that we might transcend our limits. Hope that distance and time need not keep us apart from whatever, or whomever, we love or seek to know. When we dream about wormholes, we are in a sense dreaming about breaking free from boundaries. It's no surprise that in fiction, wormholes often lead to salvation or discovery, an escape from a doomed planet, a meeting of long-separated friends, a shortcut to a new beginning. They carry a narrative weight that goes beyond their physical definition. In reality, we don't know if nature allows such benign outcomes. A real wormhole, if it exists, might be perilous or untraversable. But the dream of a gentle passage through the stars persists. It's a beautiful dream that drives us to keep asking, what if? And sometimes to attempt the seemingly impossible. As we reflect on wormholes, we also reflect on the nature of scientific progress. So many breakthroughs start with a question that sounds like fantasy. Travel faster than light? See beyond the edge of the observable universe. To the skeptical mind, these were once absurd notions. But consider how many absurd ideas have become reality over time. Flying machines, rockets to the moon, even the teleportation of information via quantum entanglement. Today's fanciful speculation can become tomorrow's accepted science, if nature permits. Wormholes remind us of this, urging us not to close our minds. They encourage a certain humility and openness in scientists, an acknowledgement that we don't yet know all that is possible. In this way, the poetry of an idea spurs the rigor of research. The dream fuels the experiment. In the end, whether wormholes turn out to be real or remain a beautiful idea, they have already served as a bridge, connecting the world of physics with the world of human imagination. They show that even in the realm of equations and data, there is room for wonder and metaphor. The universe is not just a cold, mechanical place. It is also a source of inspiration that touches our hearts and minds. Wormholes, as theoretical constructs, illustrate that duality. They are a triumph of mathematical reasoning, and at the same time, a canvas for our hopes and fantasies. They allow us to contemplate travel to the unreachable, to ponder time as a landscape we might roam. In doing so, they bring out the poets in the physicists and the scientists in the dreamers. Our journey through the idea of wormholes has taken us across a spectrum, from the very technical to the deeply personal. We've peered at equations and bent our brains around the physics, and we've also let ourselves marvel and wonder. In this meeting place of knowledge and imagination, perhaps we find the truest essence of why we explore at all. The universe invites us to understand it, but also to dream about it. As we conclude this part of our cosmic exploration, we carry with us both the facts and the feelings, the science and the poetry. The story of Wormholes is as much about us, our curiosity, our creativity, as it is about space-time tunnels. And though this chapter of the journey draws to a close, the larger journey goes on. The cosmos still holds many secrets, and we will continue to chase them, armed with telescopes, with equations, and yes, with dreams in our hearts.